Here we go.
Being conducted by Gary Cornell, Chairman, CEO of Blaco Fluid Control, a manufacturer of pulsation dampeners, surge suppressors, inlet stabilizers, and other fluid control products based in Riverside, California. With a BS degree from California Polytechnic University, Mr. Cornell has worked in the reciprocating pump industry for more than 35 years and is a member of the Hydraulic Institute and American Society of Mechanical Engineers.
Now pay attention to this because two things are going on. Hydraulic vibration and acoustic, okay? So what is this phenomenon, okay? And it's hydraulic shock, a momentary increase in pressure in a liquid system due to the sudden change in velocity of a fluid. That's the key point. It's not necessarily stopping the fluid, but a rapid change in velocity, okay? Called water hammer because it creates this acoustic sound or this pressure wave or transient, and it sounds sort of almost like a hammer banging on a piece of pipe, okay? Now, since it's an acoustic wave, and we'll talk more about this getting into it, but since it's an acoustic wave, it's not just liquid shifting back and forth, but an acoustic wave. This wave of pressure that's created travels at the speed of sound in water. Now, what's the speed of sound in air? About 1,700 feet per second. In water, it can be as high as 4,700 feet per second, this acoustic wave. And that's important for a couple of three reasons, but one of them is it's very hard for an end user or a customer sometimes to understand what's going on when a valve closes 500 feet away, 1,000 feet away, and at the pump, there's an action almost instant. Now we've got our little coil demonstration. I think most of you have seen we did that in the plant, and we can create some of that time lag in that situation. But people don't equate this acoustic wave with the reaction that occurs. So we're always emphasizing what happened, where did it happen, why did it happen, and then it's our job to figure out what to do to fix it. Okay? And a lot of things can vary, and we'll get into it a little bit more, but we call a water hammer or hydraulic shock. There's also a thing called surge, and the units usually called surge suppressors, but surge is a less intense form of water hammer, and typically happens downstream of any valve closing, anything like that, not upstream. So if we have uncontrolled hydraulic shock or water hammer, what's the potential? And you've heard us talk before, it can be to 4 to 8 times momentary increase in pressure over the normal flowing pressure. Okay, so I was a bit wrong. It's not 17, it's about 1125 feet per second, it's 47. So with the same intensity, energy pressure in water is 60 times that in air. And that's why submarines have torpedoes that explode below the water line, right? You think about tsunami and the energy that's carried for literally thousands of miles without dissipating. Water is or liquid is a very efficient transfer of energy, okay? Simple formula that's quite accurate in predicting what this pressure rise will be is using the 60 times the velocity of the liquid in the pipe, feet per second, times any specific gravity divided by time. Typically, when we're talking about water hammer and a valve closure, which is probably 85 to 90% of the applications, we're using 1 second as a valve closure time. Okay, so if we use this, and this is just a computer-generated graph of what happens when a valve closes instantly. You get an immediate spike and then a tapering off of this acoustic wave. It doesn't just stop, it reverses from where it is. When it hits another solid object, it reverberates back the other way and keeps oscillating until something breaks or the energy is dissipated through friction. Just much faster, much faster. Well, you can, yeah, now, you know, a second is pretty fast, but in terms of water hammer, it's a long time. So we're just going through exercise here, and we're saying the velocity is 6 feet per second. Specific gravity 1.2 and time is 1 second. Now, 6 feet per second flowing in a process system is not all that fast. Okay? There are a lot of places out there that are going 8, 10, 12, even 15 feet per second. Obviously, the faster it flows, the more velocity you have, the more damage that can be done. Mostly about 4 to 5 feet per second, you start being concerned about this phenomenon called water hammer, okay? So, it equals 432 PSI, okay? 432 PSI. Now, this is really important because I've been on the phone and I've heard you guys talking to customers, and the customer says, well, why can't I use a plastic dampener? My pressure is only 20 PSI, right? Low pressure system, so what? Because we don't want to use plastic dampeners for water hammer or surge devices, okay? But the problem is, this 432 PSI is cumulative to the system pressure. So you may be at 20 PSI in the system, but now we're going to add the system pressure to the increase in pressure. And if the system pressure is 100, now we're 500. Even taking that away, let's assume we've got plastic pipe, right? Plastic valves, and low pressure gauges, flanges, rated at 150 or 200, 250 even. And we're hitting it with 432 PSI above the system operating pressure. It's a formula for disaster, and it happened. Got a change in velocity rapidly, right? Valve opening and closing, pump start and stop, pump power failure, potentially one of the most dangerous areas there is, piping profile and direction change, and column separation. There are other factors that can create or increase the potential problem here in trained air, because one of the things that we know about, and we will see later on, is that for all intents and purposes, liquid is not compressible, right? But if there's a lot of air in it, or if it's hot water, there's a lot more air in it. You get the compressibility factor in there, now we've got a spring that can actually increase that spike as this water comes crashing to a stop. It's still moving, but there's air compressing in it. Then all of a sudden you get a secondary slam. You know, no. The sad thing is no. We had a young engineer that had just graduated, worked for a summer as a seminar or as a work program with Blako years ago, Eric. I asked him about that. He said, you know, in 4 years of college, we touched on this for about 30 minutes. You can't believe the number, well, you can, the number of systems that are designed without any concern or thought whatsoever for the consequences of valve closure. I took a course from an instructor several years ago who was an AHME instructor. We did a bunch of problems. And one of them I always remembered was it was a 36-inch diameter pipe, 10 miles long, and on a slight incline of 4 degrees, 3 or 4 degrees. We calculated, and you can do this, you calculate the time to close the valve, which will prevent closing it or slowing down the velocity too quickly. It took 24 minutes to close that valve, so you wouldn't have a rise in pressure. Remember, the whole key is rapid change in velocity. If you can avoid the rapid change in velocity, you don't have a problem. And of course, that's where the Blake dampener comes in, our third step. Okay. Typically, closing within 1.5 seconds depends on fluid velocity. Quick valve closure is similar to a train wreck in a pipeline. Okay, the engine stops, but these cars keep moving, and especially if there's more air in the liquid or more air between them. The first car stops, the rest of them still move until you get the big crash. I like to use the example of the crash dummy test, right? You've got this block wall, you've got a car traveling at 60 miles an hour. We'll get into this a little bit more. And the car hits the block wall, stops rapidly. Velocity changes rapidly. What happens? The energy gets absorbed in the car, right? And the test driver and everything. If you put a spring at the wall so that the car came to hit the spring first, that spring would absorb the energy and slowly decelerate the car so that by the time the car hits the wall, there's no damage because the velocity is all slowly dissipated, right? That's exactly what a Blanco surge suppressor does, and we'll talk about that more. But think about it. The valve closes, right? The liquid is coming full force into the closed valve. If we have a surge suppressor properly charged and sized right there upstream of the valve, the liquid is directed up into the surge suppressor, which is just a big spring, right? So that liquid has a place to slow down, change the velocity speed slowly, and no pressure spike is created. And you can see that in that coil that we have. Energy concentrates, it reverses direction, pressure wave moves at the speed of sound in water, hits the check valve or pump and reverses direction again, back and forth. Energy is absorbed by friction after several waves. This is a check valve in the system. And we'll do this, I think, pressure of the downstream side is usually a drop in pressure depending on what we talked about, the surge, which is on the downstream side of the valve. That's the valve closure and hitting the check valve. Most all pump systems, see there is the valve closure. Most pumping systems will have a check valve at the discharge of the pump to protect the pump when the pump is turned off. That's the check valve that was slamming. This is that whole system. So to control the valve closure hammer, slow the liquid velocity, use a slow closing valve, use stronger pipes and braces, use relief valves, surge tanks, or bladder surge suppressors. You could use any of these. The whole idea is either you're going to have to contain that energy or prevent it from occurring or transforming its makeup. I'm not going to go through all of these carefully. One of the things that you can do is control the valve closure time, but typically they say, I want the flow to stop, I want it to stop as quickly as I can get it to stop. So they use quick closing valve. You can use a surge tank which is just basically a standpipe. The problem there is you can't keep the air separated from the liquid, so it waterlogs and loses its effectiveness. The bladder surge tank is the best permanent, lowest maintenance product you can use to control this surge or water hammer phenomenon, because it keeps the gas separated from the liquid. We all know that. Just some examples of what can happen now when you're running a pump, and typically a centrifugal, but it doesn't have to be. One of the problems that can occur is when you have a pump start and the system line is full of liquid, but stationary. This is the problem. You have a big sprinkler systems. That's why there always has to be some sort of a surge suppressor in these systems, because you're starting the flow of liquid against a block wall. And when that flowing liquid hits the solid liquid, that's not compressible and you get a big bang, okay? The other situation that can cause a lot of problems is when the line's empty. Because now you're pushing liquid rapidly down an empty line that has only air in it. The air is going to move much more quickly without resistance until you reach some point at the end, which could be a reduction, an elbow, or any other thing that creates, again, a rapid change in that velocity. Then there are other problems that start making these things complicated, and that's pump profile. And you can have liquid here and then a rise. When you turn the pump off of this area, can be filled with air, then down below it can be liquid again. You start moving that liquid against air, and then it hits the solid line, moving liquid again, and you get all kinds of problems. So some of these get pretty complicated in the profile, and sometimes we have to get help doing these things, but most of the ones we deal with are pretty straightforward. Now, this is what's called rapid pump shutdown, and you're going to see column separation. This also is a significant problem, because when you have liquid flowing at the discharge of the pump down the line, and you turn the pump off, the flow stops coming out of the pump. But that fluid will tend to return or reverse and come back, because one of the main reasons is you've got a section of pipe now with nothing in it, no air release, so you lower the atmospheric pressure in this piece of pipe, and the liquid gets sucked back in. It can be actually subatmospheric. You can go below atmospheric pressure in that section of pipe from the pump as the fluid moves away from the pump. Okay? So this is what happens when you, okay, now watch this. It comes crashing back. And that's the reciprocating effect. And what happened here is that acoustic vibration reciprocating, but here we're flowing along, the flow stops, the pressure reverses, and all of a sudden we get a big gigantic pressure spike as the flow reverses back through the pump. That's happening pretty quickly. That could be a 500 long piece of pipe. This is a failed pipe underground.
Place you have to be.
How do we start? Car is going past, there's water on the ground now. That's significant water hammer. This is big. That's a truck. There's the manhole cover. It's huge. All right, I'm going to go on because so the ways you control start stop are to use air relief valves, the vacuum breakers, slowly opening, then slowly closing a valve at pump discharge, check valve at the pump discharge, surge tanks, and bladder suppressors. So the same things you can use before. Again, the goal is to have the velocity of the fluid change slowly. Slow change, you don't get a buildup of energy all at once. The suppressor acts, we talked a little bit about the spring and the block wall, but same thing on start-stop. If you throw the liquid into the line, you're going to velocity hitting a non-moving column of liquid in a spike. But putting the dampener in is like putting a spring in, interrupting the system between the pump, which is the hammer, and the rod, which is the liquid stationary in the line. The spring absorbs that rapid start of energy by allowing the liquid to go up into the suppressor and hold it there until the speed of the solid or the non-moving column liquid starts moving. It'd be like, let's say you're going to push a car and stall. You come up to it too fast, you hit the back of the bumper, you get an energy event and break bumpers, right? But if you put a spring on the bumper of the car you're pushing and then come up on and hit that spring first, it'll first absorb some energy and then start accelerating the car in front of you, and there's no damage will be done. Potentially the most dangerous situation of all is power failure, in which the pump is running, producing flow, and they lose power, which is unfortunately more common than people realize, especially in some rural areas and everything like that. What happens is the pump stops flowing liquid. And remember our example of the liquid keeps moving and then reverses direction. And it reverses, and I can't give you the formula or the exact wording of it right now, but it reverses at the same velocity it went out. So now it's reversing, it's coming back. Just as it gets to the point of the pump starts again. It's a momentary power failure. Now we have a head-on collision. So we've got the energy of this liquid coming and the energy of the liquid coming from the pump, and they collide somewhere in this area, and it's just catastrophic at that point. And again, putting a surge suppressor there is going to protect the system because it gives a spring where these two liquids come together and go up and decelerate again. Now, in all of these situations we're talking about, with the exception of downstream surge, our device needs to be placed in the direction the flow is coming. If it's coming back this way, you would have a check valve here, and it would hit the check valve and go up in here. If it's coming from the pump, then you want this to flow up into the pump, and the check valve would be downstream. Okay, so the energy side basically is where the device goes, or the suppressor goes. Pipeline profile again can get very complicated, mainly because most of the customers don't know it, don't even know the profile. But as you drive around the city, do you ever notice on some corners these kind of green little sandpipes with a neck on it and a tank? You ever see those? Inside the float on a hinge, they're designed to let air out of the underground water system, so you prevent something like that. Those are just nothing more than air release valves that are connected underground to the water system. And you see them all over the place if you take the time to look. Water hammer in my review is an acoustic pressure transient or wave. Okay? Occur whenever fluid velocity changes rapidly. And remember we talked about rapidly can start at 4 feet per second, which is not I remember doing calculations with stuff with wilderness. We'd be at 8, 9, 10 feet per second. And you've really got a potential situation for disaster when you get to those levels. One of the problems is companies, especially contractors, like to try and get a low bid. They'll undersize the pipe. Well, to get the same flow out of an 1.5-inch pipe that you get out of a 2-inch pipe, what do you have to do? You have to increase the velocity, right? Which increases the pressure, which gives you that base pressure that you're going to rise up or increase when you have this event occur. So anyway, I say 5 feet per second there. Start looking at it 4 feet. This is what we need to know. What can happen? Why will it happen? Where will it happen? And then what can we do to prevent it? The toughest thing, and the customer calls us, what size pipe is it? Well, it could be 2, could be 3. How long is it? Well, it's 4 or 500 feet long or 2. You know, we can't solve the problem unless we get some relatively decent technical information. Right? Keep digging and digging and digging. Now, this is a computer-generated profile of a valve closure. What you're going to see is this pump profile, and the arrows going back and forth with the oscillation. They'll change from blue to red, and then a graph profile of this pressure spike. Okay, now this is the whipping action. See the arrows changing as the oscillation occurs, and the pressure spike going all over the place, and then the profile up there of the pressure spike dissipating as it oscillates. And this is extreme stuff, but it happens every single day. We had one situation with Graham. This is was a diesel filling station for diesel automotive, and they had Blackmer sliding vane pump. We talked about those the other day, that they would use to pump the diesel to fill their locomotives, and these are like 4-inch long, done manually. Well, when the tank got filled, operator closed it, sent the shock wave back, and blew all of the sliding vane out of the pump. So we ended up putting, I think in that case, it was a 40-gallon unit out there. But my point is, this was all designed by an engineering firm, somebody who should have known the potential. It wasn't even considered. 90% or more of the applications we get into involving surge, and we get them almost every day, 90% of them are after the system has been built and operating, and then they find they have a problem. But after the plant opens and after the first event occurs, then they're scrambling, and sometimes it's really difficult to find a place or a spot to put the units in, because and if you don't put it in the right place, it's not going to work. Remember, we said this is traveling at the speed of sound in liquid, which can be as high as how much? 4,700 feet per second, right? So once that acoustic wave starts moving, you can't capture it. It's going to go right past the stabilizer inlet. But if you put it right upstream of the valve, within 10 pipe diameters, right, hits the valve, as it's decelerating, it's right there, it's going right up into the surge suppressor, which is the big spring. The spike never happens. When the liquid then stops, the pressure stabilizes. That liquid that's been accumulated against the gas charge just pushes back into the line. No harm, no foul, no problem. You know, that article I wrote was based on a true story at Bear Paint. So they told them, just slowly change it from a ball valve or a butterfly valve to a gate valve, like we've got on our hose pump out back. It takes about 15 turns to close it. By that time, you're slowly closing it. The velocity of the liquid is slowing down. No pressure is it. But if you take a quarter-turn ball valve and, you're stopping it quickly. There was in Ohio at a Sherwin-Williams pump. They had a Wilden 2-inch pump, bolted to a concrete pad with welded stainless steel tubing. They went up about 30 feet in the air to the ceiling, across the plant, came down, and a guy manually was filling tape. Closed that valve. It ripped that 2-inch pump off the concrete pad and turned it 45 degrees and bent that 2-inch stainless steel pipe. And the energy is incredible. And we talk about just stand in the waves and let a wave hit you. Yeah? The velocity and the mass of the liquid will knock you over.
Hey, thanks, Zach. Appreciate that. So, yeah, sorry everybody that we ended up having to give an online video. I know it's not the preferred approach to some of these trainings, but we just couldn't find enough trainers for this round. So if you, I mean, some of those videos are really good. I know people may or may not love that format, but doesn't allow for quite the same interaction. So with that said, if anybody, for future reference for next month, if anybody knows somebody that has a 30-minute presentation they'd like to share, I think these virtual setups are a great opportunity to get people that may not be able to travel here to give an excellent presentation. We can do it virtually, but great. Well, thank you. I was gonna ask if somebody had a water hammer story, but since we got started a little bit late, I don't want to steal any of Bobby's time. But if anybody has any comments or thoughts or anything, just shout them out in the chat there. But if not, then Bobby, if you're on here, we can try to get you set up, get your screen shared and your.
Yeah, let me share my screen here. Actually, it said it's disabled and the host needs to allow me to share it.
I like to call Zach a control freak, so, but no, he'll turn that off in just a second here.
All right, I just switched you over, Bobby. You should be the host.
Okay, great.
I'll try it again. Excellent.
How does that look?
Beautiful.
Looks
Okay.
good.
All right. Well, I will kick it off here. Just want to introduce myself to everyone on the call. My name is Bobby Brisky. I work for Mueller Company. We have a fire hydrant and gate valve side of Mueller, but I'm on the technology side of Mueller. So if a lot of you guys might know Bade with Mueller on the infrastructure side, but this presentation is going to be about the latest and greatest that is going to be coming down the pipe with Mueller. It's going to be our smart hydrant that will read pressure and do some leak detection. So going to do a quick overview of it, and then please feel free to ask questions along the way. So one of the big pain points that Mueller Company has identified over the last 5 years is the aging infrastructure that all utilities are facing right now. I live in Dallas, cover the South Central region for Mueller on the technology side. So I see it all the time. Every utility has aging pipes, aging workforce, not enough time in the day to fix problems or get the water quality to the high standards that we require for all of our customers. And that's what Mueller is going to try over the next 5-10 years, is to really help out the utilities by providing data sources through all of your assets. So that is the driver of what our smart hydrant is trying to accomplish, is to utilize your existing infrastructure. Hydrants are a great source of that. They're already out in the field. They're already in the downtown areas, or they're already in your most outskirts of town. So we're really going to utilize the existing infrastructure and get you to have data communicating back into your servers or into your supervisors that at that point can make the right decisions for your water system. So yeah, so the value of data is not the data itself. That is something that we've learned over time. Data is useless if you really can't do anything with it. So right now we're really trying to take that data that our infrastructure brings to us, and analyze it and change it to have kind of the ability to make better decisions. So this is kind of the quote that Mueller's using: "The power of information is unlocked at the intersection of multiple sources of data." So we really want to take a full breadth of data points, from hydrants to valves to pumps to water quality stations. We want to take that all in, because each one of those by itself is not enough to make an informed decision. So we're really going to bring all that data into a platform that will allow utilities to make informed decisions. So this is kind of a neat slide that we've been promoting. Is just, and it does not have to be Mueller products, but just think of all the different products that you have in your system, from meters to gate valves, from water quality stations. Just think right there from the hydrant, that if my pressure has dropped 15 psi in the last hour, or there's a leak 128 feet, just think if these are the questions, or these are the data points that you're going to get from your infrastructure. So it's a really cool opportunity that we have in the water industry, because I do think the times are changing, and technology is becoming such an integral part to all of our lives. I mean, it doesn't have to be necessarily in the water system. With our iPhones, you can do a lot with a phone just at any time of the day. So Mueller's going to try to be the cutting edge and provide many different options for utilities out there. And again, the smart hydrant is our really great first attempt of providing that infrastructure along with technology and meshing the two together. So this is our Centrex software-enabled Super Centurion hydrant. We're just going to call it Smart Hydrant. It's going to be utilized on our Centrex software. So Centrex is just the platform that Mueller uses to collect all of its data. So it will be transmitting its pressure readings and leak detection findings to the Centrex software. And at that point, utilities can log into their system and have all that data at the tip of their fingers. So that's where we are going to say you can really take multiple points, hydrants, meters, water quality stations, and make that informed decision, just because they do all work together. The water system has many different layers, and you can't just make a decision on just one of those layers. So this is the Mueller, the smart hydrant. It's going to have kind of the four pillars or four main items to it. First and foremost, it's going to look and feel and operate just like a regular Mueller Super Centurion. So we really wanted to emphasize that we didn't want to change its footprint. We didn't want to change its design too much. We didn't want to make it look any different. Mueller takes a lot of pride in our fire hydrants. Certainly our Super Centurion, it has a unique look. It has a look that utilities and customers are used to. And then it also has the functionality that customers are used to. I came from the valve and hydrant world of Mueller, so I've changed out many of main valves and stems and safety couplings and traffic flanges. So I understand the repairs that these hydrants can go through over time. And Mueller really wanted to keep that as similar as possible, and we've done that. A lot of what you see there is going to be the same couplings. It's going to have the same flanges. The bonnet is going to have the same dimensions, and then it will have the same op nuts up there at the top. So first and foremost, it will look and feel just like a regular Super Centurion. Next is the pressure monitoring side of it. The pressure monitor is going to be down at the shoe area, just through the main valve there. It will be able to continuously monitor pressure, and then also be triggered for transients. So if you guys have transients, it kind of goes like that water hammer video that we just watched. If it does detect a water hammer or transient through the line, it will trigger itself to be in transient mode, which is 256 readings a second. So you'll really start to see what's happening or what PSI the water is getting as that transient passes. Third is the leak monitoring. So this is going to use our we call it a DX cap. So it's going to monitor for leaks every morning at 2 a.m. So this is an acoustic correlation. So it does not need to have the water charged. The water does not need to be in the hydrant itself. It will be going through the pipe wall. So this will again monitor for leaks. You put out these nodes into kind of a mesh network of your system, and then they will correlate in between each other to try and find leaks. So this will work on all metallic pipe and AC pipe. It does not work on PVC due to the acoustics that PVC has. They just really it dampens the sound of water kind of coming through the pipe. But if you guys have metallic mains, you can put these nodes out on kind of every third hydrant, and they will monitor for leaks. So we can say it'll be 125 feet from this hydrant, 300 feet from that hydrant. And then lastly, all of this is cellular based. So it will be going through the cellular network. And so really what you're looking for is just a couple bars of this is a Verizon cellular network. So if you have 2 bars of service in the area that you want to put this smart hydrant, then you're good to go, and it will push the data that it's collecting to our servers through that cellular network. So this is really just showing what all Mueller is trying to do, and this is not limited to Mueller products. So we really want to bring all the data points out in the system into one place. That's what I was emphasizing at the very start. Just having leak detection or just having water quality isn't telling the full story of what's happening in your system. So we have the Centrex server. that's collecting all of this data into one user interface, and then it'll allow utilities or supervisors or field techs to be able to look at your phone, look on your laptop, or even get alerts saying that a pressure has dropped and a leak has happened in between these hydrants. So really wanting to bring all of it together into one, because that's what we believe is going to bring the most value and the best decisions from these data points, is if you can see the full picture. So this is a screenshot of what that Centrex platform will look like. At the top there is what the leak detection page would be, and at the bottom is a water quality station with pressure monitoring. So you see there at the top of that screenshot, there's different tabs. So that's what you'll be able to do is with the smart hydrant is tab over to leak detection, tab over to pressure management, and it's all at one click. So again, if you don't have Mueller in your system, we do believe that the best way to make informed decisions is to bring it all in. So if you have a SCADA system, that's what SCADA is trying to do. It's bring all that data into one platform so you can take a comprehensive look. So we're not trying to get rid of SCADA. We're going to be an asset to SCADA if you already have that system, because we can bring that data into a SCADA system. So a really good overview of the smart hydrant. Again, it will be leak monitoring and pressure monitoring. That will be the two options. If you do have PVC mains primarily in your system, you can just have a pressure monitoring hydrant. It does not necessarily need to have both. But for pressure monitoring, it will be a dry barrel hydrant, so you don't need this hydrant charged. You don't need water pressure up to the cap. It will all be in the closed position and in the dry barrel position. There will be no wires. It is a wireless design. I'm going to go through kind of how that looks and what the smart stem looks like. But it will be basically the data is collected from the shoe area and then Bluetooth to the bonnet, which is then going to push its data through the cellular network. So there's no wires. If a car hits this hydrant, it will break just like a normal hydrant would right there at the safety coupling. And there won't be any wires sticking out or anything like that for your customers to worry about. So it is a wireless design and would operate very, very similar to a Super Centurion. And then we offer new hydrants that already have the pressure monitor in the shoe, or we can retrofit any Mueller hydrant from 1975 to present through the 3/6 or 6-foot Berry ranges. So retrofits are something that we want to offer to customers just because the real value of the Mueller, bringing a Mueller hydrant to a smart hydrant is that hydrant's already installed. You wouldn't have to dig into the concrete. You don't have to change out any of maybe the old pipes that are coming from the main into that hydrant lead. You can retrofit a 1975 hydrant into a smart hydrant without having to change or dig too much into your system. So keep that in mind if you do have places that you want to convert a hydrant into a pressure monitor. You can do that through a retrofit kit. So like I was saying, it's going to look and feel very, very similar to just a normal Mueller hydrant. It's going to have the same NSF ratings, the AWWA ratings. It's going to have 350 PSI working pressure, and then that pressure sensor will go up all the way to 250 PSI. It has a 10-year battery life, and in something that in our other product lines, 5 years is kind of the standard battery life, but we have doubled that to 10 years. So it's something that if you install one of these retrofit kits or a new hydrant, it's something that you wouldn't have to maintain or change out for the next decade. So that goes along with just the Mueller brand. We want things to last. We want things to live quite a long time, and that's kind of falling right into that value. So you see here, so this is what the components will look like. You see there on the left, so the bonnet will have the battery and the antenna, and the cellular storage area. So this is where the data that is collected from the shoe will push into the servers and into the Centrex platform. So the bonnet will look exactly the same. It's going to have the same dimensions. It will have the oil reservoir, and something that customers or yourself might not know. This is a smart bonnet until you actually take off the hold down nut and op nut. You see there right in the middle, and then on the right is our smart stem. So this is a Bluetooth connection. So this is where I was saying we have a wireless design. There's no wires going from the shoe all the way up to the bonnet. It is that data is going to be transferred via Bluetooth. So there's their Bluetooth receiver up there in the middle of the bonnet, and then there's a Bluetooth antenna just underneath the safety coupling. So it's something that to not have wires will make the flow supreme, and then will also, if you are working on the hydrant, it'll be a very normal fix if you are trying to change out a main valve or a safety coupling. So the leak monitoring cap will also look very similar to a pumper nozzle. It's going to have the threads that your utility uses on a regular hydrant, and then also the op nut will be similar to what each utility has for their hydrant fleet. And then sandwiched right in the middle is the processor, the battery, the antenna, and then the acoustic sensor. So it will really only stick out a couple inches from a normal hydrant cap, but it will look and feel very similar to just a normal Super Centurion cap. You see there the middle, the smart stem. They'll have a Bluetooth antenna. They'll have the pressure sensor there that will go through the main valve into the lower part of the shoe, and we'll be able to get pressure from the closed position. And then you see there a smart bonnet. It's going to look and feel, have the same I guess look as the Mueller bonnets. It will have the opening direction. Will have where it was made in Albertville, Alabama. And again, we'll have that oil reservoir where you can put food grade oil into your Mueller fire hydrant. So just kind of finishing up here, I think I'm almost 22 minutes or so we'll have some time for questions. But really just want to showcase what Mueller's trying to do, certainly for the future of our products. We're going to make the highest quality valves and hydrants, but also add kind of the ability to collect data from these points. Because like I said, data is what what's improving in our water industry. Collecting data from the water system and making decisions with it is the future, and it's something that we believe we're going to be on the forefront of this kind of revolution in the water industry. So with that, it will reduce water loss, it will reduce your energy consumption and liability that again leaks or transients can cause in a water system. So we want to help out in every way we can. So I think with that, we'll just open it up for questions, because I don't want to go over if people have time here.
Yeah, does anybody have any questions for Bobby? Bobby, you answered my question on that screen right there, so about the battery life for different types of use. So
okay, yeah, no,
you beat me to that one.
Yeah, so 10 years is the standard. You can put it into full transient mode, which will, again, it reads at 256 readings a second. So it will drive that battery down, but you can switch and toggle that transient monitoring. So you can do it for 5 minutes a day, or if you know a pump's kicking on at this time, you can turn it on for an hour just to make sure. But well, no, I appreciate everyone's time. Again, my name is Bobby Brisky, and I'm on the Mueller technology side. So please feel free to reach out, and we can have a conversation to see what we can do to help each utility in this area.
Cool. Thanks, Bobby. Anybody else got any questions? Great. Yeah, Bobby, you don't have to, but you're welcome to put your contact information in the chat there. That way people can snag it easier, and it'll kind of be there for the day. But great.
Excellent. All right, I'll do that right now.
Cool. All right, great. Thanks, Bobby. So,
yep, thank you.
All right. Well, we'll take a quick break. Just we'll probably start a little bit before 9:30. Probably end up starting around 9:25. Yeah, look for Bobby's contact information in the chat there. And let's see, Becky, I think I saw you join there. If you are ready, we can get your presentation kind of on the screen and make sure it works, then give a few minutes before we start.
Hey, good morning. Can you hear me?
Yes.
Wonderful. Okay, I think if you could help me have the ability to share my screen.
All right, I've made you the host, so you should be good to go.
Thank you.
Oh, is that you in the picture?
I'm sorry?
Was that you in the background?
Right there?
No. No, that. Is that you?
No.
Oh, okay.
No, that's just your good old stock image there.
Oh.
Maybe someday. Well, you just let me know when to start and we're good to go.
I think, what'd you say, Mayo? 9:25?
Does that work? We'll wait 5 minutes, give everybody a chance to take
coffee.
a quick break, and then 9:25. So
sounds good.
All right, we'll bounce back on, and so just a few minutes. Just one more minute there, everybody, and we'll get started in just a minute. Okay, we will. Yeah, thanks again, Bobby and Becky both. We really appreciate your support, offering your expertise and your time, and helping keep the water and environmental program moving here in Northwest Arkansas. We really appreciate it. But if you are ready, Becky, then we will just let you have it.
All right. Well, thanks for having me here this morning. And I'm kind of sad we're not all out in Lincoln hanging out and having snacks and visiting, but this is fun too. So thanks for having us online for this presentation. So again, I'm Becky Roark, the Executive Director for the Beaver Watershed Alliance. And our topic today is going to be learning a little bit about the Beaver Lake watershed and some things we're doing to protect our source water supply, which is Beaver Lake. Okay, so our mission as a nonprofit is to proactively protect, enhance, and sustain water quality in Beaver Lake and the integrity of its watershed. And we do that through education and outreach, technical assistance, and scientific monitoring. We do have a small staff, but we have some people that are focusing on specific things like agriculture, GIS work, water quality. We have an outreach coordinator, and we're looking to hire a stream and forest resource specialist. We're also guided by a 20-member board of directors. And these folks all represent different stakeholders within the watershed area, government, construction, education, conservation, water utilities. So we really appreciate our board of directors. And, we just want to talk about the importance of Beaver Lake. So it is our drinking water source for over 500,000 people in Arkansas. It provides hydroelectric power. It's a recreation and tourism hotspot for the state. And Beaver Lake is a cornerstone of our community growth here and economic development. Now, back in 2010, the Northwest Arkansas Council got together and put together the Beaver Lake Watershed Protection Strategy. And this strategy essentially outlines goals to help maintain a long-term high-quality drinking water supply, to help restore water quality of impaired areas within the watershed, but also it's intended to help minimize additional costs and regulations for people living and working here. So if we follow this guide and can do best management practices within the watershed, it can have a financial benefit, not only to utilities, but to the residents that purchase water. And this strategy was the first modern 9-element management plan accepted by the US EPA. And Arkansas does have a state priority watershed list, and Beaver Reservoir is one of those, along with the Illinois River to the west of us. And there are segments that are listed on the 303D list. Those are defined every 2 years by the Department of Environmental Quality. And those segments, we're just looking at trends and things over time, and also helps guide our work on where we could do best management practices to proactively prevent future segments from going on the 303D list, but also try to address some of these impairments and repair or restore waterways. So sediment is the #1 pollutant to Beaver Lake, and we call that a non-point source runoff because you can't point specifically where it's all coming from. It's coming from several different sources. So dirt roads or stream channel erosion, or maybe ag runoff or construction runoff. These are the different sources of when it rains, sediments flowing off the landscape and into a nearby waterway. And with that sediment, it can carry phosphorus and nitrogen, which can cause algae growth in our waterways. And so that algae growth is expensive to remove from water utilities, but also can have effects on aquatic species and humans. And our strategy has identified areas of high priority for sediment reduction, and that includes the area adjacent around Beaver Lake, the lower White River area you see here on this map on the left, and the West Fork watershed. So these 3 watershed areas are our priority for reducing sediment, closely followed by the War Eagle watershed. And the chart on the right, this is using modeling and data to show us that channel erosion is the largest contributor of sediment, but in the near future, low density development is expected to increase and contribute more sediment loading to our waterways. So something to think about as we grow and develop, how we can protect waterways as we do that. Northwest Arkansas is a rapid growing region, and especially there in the core, the western side of the watershed, and the eastern side of the Illinois River. That's the Rogers, Springdale, Fayetteville, Bentonville area, growing very rapidly. And, last we heard 32 people were moving to Northwest Arkansas per day. We're expected to have over 1 million people by 2040. So just to kind of go through some of these different things we're doing to help address water quality in this area. Our best outreach method is to reach landowners directly. So we mail out newsletters to them directly. So if you live in the Beaver Lake watershed, you may have seen our newsletter or get that 3 times a year. And we try to put information in there for landowners and how they can take advantage of programs or how we can help them manage water on the property. We also have an e-news that we send out every month that has a lot of information on events and things to participate in, or just general updates. We're on social media. We host a quarterly speaker series covering topics for water quality professionals. We have a annual Beaver Lake Watershed Symposium each year. And we also do a number of public speaking events like this, best management program workshops, and we also have youth programs as well. Okay, so technical assistance. Let's see here, click. So one thing we're focusing on is helping landowners to assess their properties. So if we have streamside, ag, forest, and urban areas, we're out there working with those folks to help them have some type of plan to follow. Oh, I guess since I'm the host, I can let people in and out, right? Somebody's coming in. And we also help landowners connect with other state agencies to get forest management plans, wildlife management plans, and nutrient management plans. So those are things that we work with partners on. We can do these site assessments on properties. And then ultimately, we try to connect with local, state, and federal funding programs. We're out also planting native trees, especially along waterways. We want to get vegetation back into those areas that have been cleared. We work with volunteers to remove invasive species. And we also help communities install low impact development. And LID is essentially landscape features that help water soak into the ground naturally versus hard asphalt, curbs, and pipes. So here you see, this is over at Hickory Creek Boat Launch in Lowell. We're installing a large permeable paver parking lot. And this is going to allow the water from all the boats and things to soak in and make sure any of those oil, grease, heavy metals and things are captured and collected and filtered instead of running directly into Beaver Lake there. We work with partners to also measure stream erosion rates to learn the sediment loads coming from specific areas of the watershed. This is a project with the Watershed Conservation Resource Center. We came back in, this is the same spot here. You can kind of see that River Cane in the back as a point. And through funding with the West Fork White River Initiative, the USDA program, we're in year 5 of that. We're able to help these landowners restore these waterways. And, you know, these restorations are done in a natural way. So they use a lot of plants and rock and trees and things. So it not only stabilizes the bank and prevents sediment from going into the waterways, it's also providing a lot of other benefits like fish habitat. You know, the West Fork water has, they've lost over 2/3 of their aquatic species. So they're trying to bring back the smallmouth and largemouth bass to these rivers. So these types of restorations can help with that. It's also helping the landowner. You know, with the price of an acre in Northwest Arkansas today, losing land is not a great thing. So, you know, we've had some landowners report losing up to 4 acres of land per year along these riparian areas. So when these areas are restored, it helps keep that land intact, but also helps improve water quality. And we do help with waterway cleanups. We work with groups all throughout the year to host cleanups and things. So if you get on our newsletter or a mailing list, we can make sure and keep everyone informed on when those events are. And we also conduct scientific monitoring. So we do serve on a harmful algal bloom work group for the state. We are contracting with the University of Arkansas to monitor water quality in the West Fork. We help support a stream gauge at the White River over in Bunch Park at Elkins. We help with pond sampling. We participate in Secchi dip-ins and Secchi Day with Beaver Water District. And we're monitoring ponds, streams, and we're also doing a lot of studies on before and after best management practices installations. So some of our current initiatives for this year are, as I mentioned earlier, the USDA program for the West Fork. We're in year 5 of that. And we're really working to technically assist these landowners. Over $8 million is being invested in this watershed to improve water quality. We're also focusing on research and development of BMPs, like this pond you see here, looking at ways to retrofit or redesign ponds so that they reduce peak flow or reduce, to reduce flooding downstream. And we're looking to increase materials for BMPs. So here you see high tunnels. We're actually working with 15 producers to help grow native plants. Oftentimes these restoration projects require native plants, and we have to go to other states to go find those plants. So having a local genotype is really important for our ecosystems here in Northwest Arkansas. So to have producers growing these native plants and making them available to the public and these conservation groups that are doing this work, we feel is really vital to success here. We're also working to expand our understanding of sub-watershed level issues and challenges. So another grant we're working on is in the Fresh Creek and Roberts Creek area. And, you know, those are smaller sub-watersheds. So we're looking to kind of scale down and start learning some issues at a smaller level. We do work with a number of partners, and we appreciate our partners that help fund these activities, but also our partners that help provide their time, their resources, their expertise. We just work with so many people, and it really does take a group to work together to achieve these big goals. So we want to thank all of our partners that help keep Beaver Lake watershed clean and healthy. Okay, so if I have a few more minutes, I'm going to cruise into the watershed tour, if that's okay.
Yeah, sure. Cruise on in.
Okay. Well, before we go there, again, I'm Becky Roark. This is my email, phone number. Call me anytime, email. We do have a website we're updating actually right now this year. And we recently moved to Elkins, Arkansas. So we're there right on the White River, which will be really nice to have folks out to show them things they can do to help restore the watershed area. We're on Facebook, Instagram. We started a podcast this past year. And as you all know, last year we had to pivot to online trainings. So now we have this really great archive of YouTube videos ranging from forest management to some of our speaker series to river restoration. There's some really great topics that are on our YouTube channel. So go check that out. Okay. All right, can y'all see that?
Yes, ma'am.
Okay, I won't go through all of this. This is a really big story map, but I thought it'd be interesting just to kind of show you all some of these sub-watershed areas in the Beaver Lake watershed. But first, this may be a refresher for some of you, or this may be old news, but we always just want to include what a watershed is. It is basically like a big bathtub. Water's draining from a high spot to a low spot. We try to think of them like bathtubs. So our drain here is Beaver Lake. So all the land that surrounds Beaver Lake, that's draining right into our drinking water source. And typically, you know, over in the west, you see ice-capped mountains that are flowing water downstream. But here in the Ozarks, because of our geology, water actually springs up from the ground and it flows and joins nearby creeks and streams until it starts building and building and building larger river systems. And we're part of a larger picture. So if you zoom out, we're part of the Mississippi River Basin, and all of this land drains straight to the Gulf of Mexico, which you see here on the left. So anything we do here in Arkansas is eventually going to reach Gulf of Mexico. The White River watershed, just zooming in a little bit, the White River itself is 722 miles long, and it's a major tributary to the Mississippi River. And this watershed drains 27,000 square miles of land. So it's a huge watershed area. And Beaver Lake Dam is the first of 3 dams that are along the White River, followed by Table Rock and Bull Shoals. And Beaver Lake is actually the youngest of these 3 dams. So it's pretty neat to think that the White River really starts here in Northwest Arkansas, on places like Mill Creek and these small creek areas. But by the time you get over to Calico Rock, which is over here, just south of Mountain Home, the rivers have joined, and now you're looking at a large White River system. The Beaver Lake watershed encompasses over 1,000 square miles, and it covers portions of Washington, Benton, Madison, Carroll, Franklin, and Crawford counties. The greater Beaver Lake watershed area stretches beyond the dam and includes the Kings River and waterways draining to Table Rock Lake. But our strategy and our focus is basically from Beaver Dam, which is located about right here, everything upstream here. So the sub-watersheds, watersheds are nested within watersheds. We could get very small with these, but these are the 7 sub-watersheds that we focus on. And that includes the headwaters, the War Eagle, Richland Creek, the Lake Sequoia or East Fork of the White River, the Middle Fork, the West Fork, and the Lakeside area. So here's some of the things I'm kind of going to breeze over for time purposes. But the headwaters here, that's mostly forested area. And that's like the main community down there is St. Paul and Pettigrew, Combs. This is the headwaters area. And it's mostly forested. And we've done some assessments on this showing it is highly erodible lands there. Mostly forested, and we've identified some stream erosion issues. The War Eagle subwatershed is the largest, draining to Beaver Lake. In fact, 1/3 of Beaver Lake is the War Eagle water that's coming in. So that's pretty amazing to think of it like that. It's also highly susceptible to erosion there because of our steep slopes. It is partially forested and pasture lands. And we've also identified a number of unpaved roads that are within this watershed area. And there's a really neat story about War Eagle and how that was named. It's actually a very tragic story about a Cherokee chief's son. His name was War Eagle. He fell in love with this girl. She was kidnapped by a trapper, and everybody ended up dying, basically. And they named this river after the War Eagle. There's a whole documentary on it. It's very interesting, but it just also goes to show you the rich history of Native Americans and settlers that are in the Ozarks here. Let's see, Richland Creek here, also very steep and highly erodible soils. Again, it's mostly forested. About 55% is forested, and about 36% of this watershed are pasture or hay areas. Number of unpaved roads identified here as well. But you see here, these are the issues we're dealing on Richland Creek. These large stream erosion issues. We get calls from landowners quite often on these things. And if you've ever been to Twin Bridges, that's where Richland Creek and the White River come together there. So another thing about these rural watershed areas is that there's a lot of septic systems. So, there's programs that are coming out that can help through the state and local groups that are helping to address septic system repair and replacement. So that is something that can help improve water quality. And I thought this was interesting. There's over 7 rural fire departments that serve this Richland Creek watershed area. Goshen, Wesley, Japton, Elkins, Round Mountain, St. Paul, and Bohannon Mountain. They help cover those areas through the volunteer fire departments. And this is important too, because as Northwest Arkansas grows, more people are moving to these rural areas. So that means more housing and demand for new infrastructure. So there's going to be a need for more rural water service providers, fire departments, things like that. So it's important to work together so that we have these resources for infrastructure. That's a really nice picture of Richland Creek there. The East Fork of the White River here, you're going to see the main city being Elkins here. Again, mostly forested. You see kind of a pattern here. The Beaver Lake watershed is actually 70% forested. So we have very steep soils, or steep slopes, sorry. You know, Lake Sequoia is within here. Oh, and what's interesting here is this is about 70,000 acres of land that's draining to Lake Sequoia. So if we think about Lake Sequoia and the water quality there, you know, that's a large amount of land that's draining to that lake. So it's important to do best management practices and manage water here for Lake Sequoia as well. And this is Lake Sequoia out here. If you've been out there, there's actually an old bridge you can see, which is the bridge that went over the original White River Channel. So it's pretty neat to see, you know, that's how big the river was at one time. And so it's really neat to have these little pieces of history that are still within our watershed. So the Middle Fork, a pretty rural area, the community of Black Oak out there. And again, mostly forested area, very erodible soils. And the West Fork to the furthest watershed here is the West Fork of the White River. And, you know, this is important because this is where a lot of development's going on. So, you know, Southern Fayetteville, Greenland, West Fork, all the way down to Winslow. So that's the West Fork watershed area. It covers about 80,000 acres. And there are segments on the West Fork that we saw earlier that are on the 303D list. So we're working with a lot of partners to address sediment and runoff issues happening in the West Fork. And again, it is a priority watershed. Okay. And then the lakeside area, saved the best for last here. This is a pretty large watershed also. It's covering 200,000 acres. That's all draining to Beaver Lake. And Beaver Lake itself has 487 miles of shoreline. That's pretty interesting. And this is, again, this is our drinking water source for Northwest Arkansas. There are 4 main intakes for water supply on the lake, and Beaver Lake, we drink it every day. And just a little interesting history, Beaver Lake is actually not named after a beaver. It is actually named after the community of Beaver, where it was built. So the Army Corps of Engineers, you know, they decided to adopt Beaver Lake or Reservoir as the official name. There is some interesting history underneath Beaver Lake, including a bridge to nowhere. This is around the Lost Bridge area. This is actually underwater now. The community of Montagnais is also partially now underwater. And sometimes when the water's low, though, you can see some remnants of that community. And Beaver Lake Dam itself, you know, this came out of the Great Flood of 1927. So it was pretty tragic and pretty devastating, you know, and then flood awareness and flood control became a need. And in 1927, the Corps of Engineers changed their flood management strategy. And in 1966, Beaver Lake became the last reservoir built on White River to help reduce flooding downstream. And it was also built for drinking water supply. And Beaver Lake is a man-made reservoir, but it is full of habitat for smallmouth, largemouth, catfish, all types of fish for recreational opportunities here. So just want to wrap up with talking about ways you can protect Beaver Lake, our source water drinking supply. You can help volunteer by help cleaning up litter and debris and trash. You can help remove invasive plants like honeysuckle and privet and important landscapes along waterways. You can plant seedlings with us. We have a number of events where we try to get out and have volunteer groups plant trees and shrubs and things. Or on your own property, you can incorporate streamside vegetation or filter strips. I'm sorry that picture's not that clear, but and low impact development using native plants to the Ozarks, permeable pavers on your driveways or in parking lots and things, using more natural infrastructure to help soak in water. You can manage your forested areas. There's a number of agencies here that help with prescribed burns and forest management, which does help water quality. And if you have pasture lands, you can aerate your pasture, which studies have shown that it can help water infiltrate into the ground and reduce runoff. And of course, you can always attend Alliance programs, events, and just stay in touch with us. So, okay, well, I'm going to pull this one back up here. If this will. Okay, so that wraps it up for me. If there's any questions, I'm happy to answer those. Or again, thank you all so much for having us here today. And we are just really excited about the things going on here in Northwest Arkansas and all the great partnerships and investments that are happening to protect our source water supply.
Thanks, Becky. Does anybody have any questions for Becky?
Bird cry. Yeah. I saw Gary on there a while ago. Gary King.
Okay, so hey, yeah, I mean, I will say I haven't been to all the sites that like all your stream bank restorations, but the ones that I've seen, very, very well done, very neat. A great thing to do. Becky, you don't happen to know off the top of your head when your next volunteer event is, do you?
We do have a riparian workshop happening tomorrow that's going to cover ways to enhance your riparian. And then on Friday, we have an invasive plant removal happening at Kessler Mountain. And that's going to take place at 3 p.m. to 6 p.m. And April's coming up, so we're going to have a lot of stuff happening in April. So stay tuned for those.
Great. Well, yeah, we're welcome. We'd love to help spread the word on that stuff. See if we can get some district members involved. So that's neat. So yeah, let's see. Anybody else have questions for Becky?
This is Amy with Beaver Water District. Hi, Becky.
Hey, Amy.
That was a really good presentation, and I enjoyed it. I always am reminded of some things and learn a little tidbit here and there that I forgot about or didn't know. But one thing I wanted to share is to encourage everybody to really keep an eye on the Beaver Watershed Alliance Facebook page. You will find all of those volunteer events, and you can note that you're interested and reach out to Becky and her staff. It's a lot of fun, but it's also such a rewarding thing to do, be outside and be helping to protect our drinking water and water quality in Northwest Arkansas.
Thank you, Amy. We appreciate that. And we just put the Facebook link in the chat over here for you if anybody, not to take you away from it, not to get you on Facebook, but it's there if you'd like to check it out and join.
Okay. Well, thanks, Becky. We appreciate it very, very much. Yeah, Misty has a question about Earth Day.
Yeah, we're working with the city of Fayetteville on we helped with a management plan for Mount Sequoia there. It's a forested open space area in an urban town. And to continue to build on those efforts, we're looking to do some invasive species removal, but also some native plantings on Mount Sequoia for Earth Day. So we're still in the planning stages for that, but we know that's what we're probably going to be doing this year. So.
Sounds great. Good question, Misty. Thanks, Becky. So, all right. Yeah, we'll really appreciate it, Becky. Everybody check out that Facebook link. And we'll take just 5 quick minutes here. We need to change some settings for the Zoom meeting real quick. And then after that, I see Rusty's on. Rusty, once we get these settings changed, we'll get your presentation pulled up and go from there. So,
Well, thank you again.
Rusty, thanks for your patience. Just a couple more minutes there. Okay, Rusty, if can you hear us?
Yes, sir.
Great. Well, we can try to. You should be able to share your screen. If you're ready there, get your presentation pulled up and.
All right, you guys
yep.
see that?
I can see it. We can see it. We can hear you. So
Okay.
we will turn the time over to you. Thanks.
All right, thank you. Hey, I just wanted to kind of give a real quick background. This was a presentation that I gave just a month or two ago for a similar event in Texas. And it was kind of case studies of nutrient removal plants, or really the operational strategies and optimization. So today we're going to kind of do a case study of the Sulphur Springs, Texas wastewater treatment plant and just kind of go through the history of that project and kind of just get some insight into, you know, how engineers think a little bit, I guess, how we go from data to what our design criteria is and some of the things that we consider, and then how we, at least in this project, we tried to look ahead and think about some future goals that were going to be required for at some point in the future. And how could we kind of marry those into a current project that would still give the client or the city some benefit? So I guess this is me. Here's a picture, Rusty Tate, served as Garver's process team leader. Been at Garver for about 12 years or 11 years, and previously worked some operators at a utility. I know recognize a lot of names on this call. So today we will discuss how a biological nutrient removal approach was implemented at Sulphur Springs, Texas. So it's kind of my 3 points here. We're going to go through some project background, ultimately how we landed on a BNR scenario, and then some of the things that we did from an operations flexibility standpoint that really made this facility ready for the future, I guess. So next slide, project background. So Sulphur Springs, Texas faced an immediate need for aeration improvements. So what we had here was a conventional activated sludge plant that really just had a series of C-star reactors, and they were all operating in parallel, and we had mechanical aeration. And this is a picture, and I'm sorry, apologize for the graininess of this graphic, but this was an existing 5.4 MGD wastewater treatment plant that operated, again, as conventional activated sludge. You can see here, we come in, we have a lift station, we have a flow equalization basin there on the bottom of the screen. We had a headworks facility with grit removal, followed by primary clarifiers, and then again, the activated sludge system. And we have a north train and a south train. And it's probably a little bit hard to see with the graininess of this graphic, but you can see there's 6 individual cells on the north and 6 individual cells on the south. And each cell had a dedicated surface aerator or vertical turbine mixer. And all the primary effluent flow kind of went into this center channel and then was dispersed equally. Well, it was supposed to be equal. We know it wasn't. The flow split was definitely a concern. But each of those 6 cells in the north and the south were supposed to get the same amount of flow. And then effluent or mixed liquor would flow over an effluent weir in each cell down a common channel on the outside and then go to the clarifiers.
What is that? Sulphur Springs, Sulphur, Texas, I think he said.
Yeah, Sulphur Springs, Texas. And then we had filtration. We ended up with, that was already at the plant, and then chlorine disinfection, just with the chlorine contact basin. So that kind of sets the stage. You guys still hear me? My computer just flashed and.
Loud and clear, buddy.
Okay, good. Well, all my Zoom stuff just went off my screen, so I was worried about that. I'll keep going. Okay, and then for solids handling, digesters, we didn't really do anything with solids handling as part of this project. But when we got in here and we looked at the data, we found that large industries introduced high organic loads into the wastewater stream. So the graph on the left is a pie chart that shows the total flow, and the dark blue is non-industrial flow, and the light blue is the industrial flow. So what we saw at this specific plant was that 70% of our flow coming to the plant was from a municipal type source, 30% from industry. But then if we switch over and look at some of the loadings from a COD basis, same color scheme, dark blue non-industrial, light blue industrial, over half of our COD coming into the plant was from an industrial contributor. So that made it really kind of told the story of why the existing plant was having the issues that it had. And so the industrial loadings contributed to abnormal loading rates. So this is our maximum month design influent concentrations. So on the bars, we have in the light blue COD, dark blue BOD, and the gray is the TSS. And then on the y-axis here, we have the concentrations of those constituents in milligrams per liter. So based on our data and our design criteria, our design COD was almost 1,000 milligrams per liter, which is crazy high. The BOD was about 450 milligrams per liter, and the TSS was over 600. Now, this was a very interesting scenario, and I know that a lot of utilities or a lot of cities face the same dilemma. Sulphur Springs had a big dairy industry in town that created a lot of jobs for the city. And they did have pretreatment ordinances, but it was into the area where the pretreatment ordinance, the utility or the industry just paid the surcharge. Surcharge wasn't really enough to cover the cost overruns, but there was a lot of political pressure to not press back on the industry too hard with fear that they would leave the town, and it was a very big source of jobs for the city of Sulphur Springs. So we know that can always be an issue, and that's something that had to be considered in this particular facility. So these increased loading rates overloaded the existing wastewater treatment plant. The flows didn't necessarily come close to the design capacity, but it was the loadings. And Sulphur Springs, they received notice of violation from TCEQ for TSS, ammonia, BOD, pH, chlorine residual, and it overflows they had in the system. So they entered into an agreed order, which meant, hey, you have to go do an engineering report and really figure out what your problem is. So I like to show this slide. So an anomaly was discovered before we even started the design process. So on the y-axis here, the x-axis, you have dates. So this was a project that we started the study on back in 2015. So it's a few years old. So you can see this data range is January of 2010 through June of 2014. And then what we see on the x-axis or the y-axis is the raw influent loading. And that's in pounds per day. So that ranges from 0 to 50,000 pounds. And so in the blue, we kind of have our rolling 30-day average of BOD loading. In the green, we have our rolling 30-day average of COD loading. And then in our, I guess that's a brownish orange color, we have our rolling 30-day average of TSS loading. And something I just want to point out here is when engineers, when we start working on projects, we always ask for a lot of data. And I know that we always ask for more data than is really ever available. And a lot of times as operators, you may be wondering, well, what in the world is the engineer going to do with all this data? Why do they need it? Why are they asking me so many questions? And the answer is really simple. We use this data to set the design criteria for the path forward. So we look at historical trends, and we know in this particular case, we had this, April of 2014, we had some very, very, very significant maximum month loading peaks. And that's important because normally our effluent permits are based on a 30-day average. I think a misnomer in our industry is we always think about, well, if I have a permit from the state of Arkansas, everything back calculates to, let's just say 10 MGD, that I have a wastewater treatment plant that's rated for 10 MGD annual average daily flow. And that can be a true statement, but what we know is that we have to meet those limits every month. So we really have to be able to treat our maximum month loads. So you'll hear engineers sometimes refer to a design capacity as the maximum month treatment capacity. And that's what we're talking about here. So if we just look at this data, as is, we would be taking these really high peaking numbers and using that as the basis of our criteria because we know this has happened. We saw this happen, and we're really looking for good reasons to get rid of this data if we can. So that's why good notes, anything that happens in the field that could have led to some of these excursions are extremely important and valuable in an engineering design or feasibility study. So what we found when we looked at this specific data set for Sulphur Springs is they had a disruption at their wastewater treatment plant. Their water treatment plant, their residuals handling system went down, and so their backup plan was to send all of the residuals directly to the wastewater treatment plant, and that happened for about a 3-week period, and so that's why we saw this very high spike. So knowing the why behind the data, we were able to discard that data and consider it an outlier, and that was not used in the plant design criteria, as it would have led to a really crazy over-designed plant. So planning efforts at Sulphur Springs focused on current conditions as well as future projections. So again, this was a 5.4 MGD average day wastewater treatment plant by permit. But our top graph here, our top table, is the primary effluent characteristics. So the first column, current average day, the third column, I suppose, the current average day loading conditions. That was kind of a roll up of their primary effluent on their current data. So a flow of about 2.82. So you can see we were barely even halfway to our average day conditions on a flow basis. And then on an average daily basis, our BOD and our TSS, 6,000 or 7,000 pounds per day, 5,500 pounds per day, and then ammonia at 427 pounds per day. So on average, that kind of took us back to about a 275 milligram per liter BOD loading. Then whenever we start thinking about our design peak month conditions, because we're not going to design a project, we want this project to have a 20-year life cycle. So we're not going to just look at today's flows and today's max month conditions. We want to look at what that design max month condition is. So we effectively looked at some growth projections and really decided, and through coordination with the city, that there was really no issues or no growth projections over the next 20 years that would make us exceed that original 5.4 MGD average daily flow design criteria or capacity. So we didn't have to do any revisions to the permit. But I do just want to point out that our design peak month loading conditions are significantly higher than what they currently saw at average day. And then down to the bottom table, our design effluent limits. At this particular facility, the current permit had a pretty standard CBOD effluent limit, 5 in the summer, 10 in the winter. TSS is similar, 12 in the summer, 15 in the winter. We were trying to hit an ammonia of 2. And while TP is highlighted here in red, while we knew going into this project that they did not currently have a phosphorus limit, the state of Texas has kind of adopted it's not officially adopted. I shouldn't say it's been adopted. The general discussion in the state of Texas is that at some point, all facilities will probably have a 0.5 milligram per liter total phosphorus limit. So we wanted to keep that in the back of our mind, because that would surely happen in the 20-year planning period that we're looking at. And we wanted to make sure that any money or anything we spent in today's expansion project really set us up in the future to achieve that 0.5 with really minimal rework. And if there was anything that we could work in today, we wanted to do that. So we evaluated multiple alternatives to set Sulphur Springs up for a future BNR plant. So we're going to take just a few minutes to kind of talk about how did we actually land on a BNR facility when it wasn't actually required. So I can promise you that we did not start down the nutrient removal path. Our evaluation, we say outside the box, that's just for graphic purposes, but we looked at several different items. We looked at chemically enhanced primary treatment because we knew the bulk of our problem was the high BOD loadings and TSS loadings that came in on that peak month basis. And if we could do something in our existing infrastructure to take out more of the BOD and more of the TSS in the primary clarifiers, we wanted to do that. We knew there could be some improvements to the aeration basins. You'll see a slide here in a second that their existing surface aerators just did not provide the oxygen that was required. And so could it be as simple as CEPT plus some aeration basin improvements? And we threw out the idea, well, if we could fit it in, we could go in and put in an anaerobic selector zone. And maybe that would help us today and provide that flexibility and that benefit for future BNR. So the first alternative we looked at was CEPT, so chemically enhanced primary treatment. And it reduces the organic loads to a wastewater plant by introducing a coagulant. So we had looked at a potential injection point at the chlorine or the primary clarifier splitter box. And the thought here was that we add the coagulant, we drop it out, we remove the BOD and the TSS through the primary sludge, and so that our loading onto our aeration basins is decreased. We know that CEPT would require capital improvements. We would have to put in a chemical storage and feed area. We do know that based on feeding a coagulant that we will increase our primary sludge, and we have to know, we have to make sure that our solids train can actually handle that. And then we put in here increased corrosion. When we did the benchtop study, ferric was the recommended, ferric performed the best as far as a BOD removal. And so if you're going to think about ferric or anything like that, then we have to be concerned with increased corrosion. But spoiler, we did do jar testing and we really confirmed that this was not a viable option. And all that goes back to the fact that I mentioned there's a big dairy industry in the town. So a lot of the BOD that we saw coming into the plant was soluble BOD. And the primary clarifier really works by taking out the particulate items. You know, we add that coagulant, we stick particles together, we settle out particles. And so if there's any particulate BOD, that would come out in the wash. But since this was primarily soluble, we didn't see enough of a removal with chemical treatment to really solve our problems. So we had to look at another route. So since the CEPT results were not promising, we turned our attention to the biological treatment process. And the first thing that, based on the high BOD loading, we did the back of the napkin airflow calculations and the aeration basin volume. It was a staggering high amount. Most plants don't see a 500 milligram per liter or 600 milligram per liter BOD coming into the plant. If you remember, our design criteria was 394 or 364 milligrams per liter, and that was coming off the primary clarifier. So we'd already removed about 20%. And we knew that the existing biological process had some severe limitations, but we had a hunch that it would prove to be valuable with some enhancements and some expanded volume. So I kind of alluded to this earlier. The existing surface aerators had limitations. So this picture here is simply a picture of one of the surface aerators and one of these single C-star reactors. And the graph here on the left is some actual DO data from one of the times we were in the field and took some samples. And so what you see on the bottom for the bars, the N1 through S6, those are the different cells. So north train cell 1, south train cell 6. And then on the y-axis is the DO in milligrams per liter, ranges from 0 to 5. And what we saw was obviously the flows weren't distributed very evenly, or the loadings weren't distributed very evenly, because in north cell 6 we had ample DO, above 4. But let's just say in north cell number 3, the plant struggled to maintain a DO above a 0.5 milligram per liter. So we knew no matter what we were doing, the surface aerators had to go, and it had to be replaced with a fine bubble aeration system. So we use biological process modeling to confirm blower sizing and basin volume requirements. We can do all this, take out some textbooks, get some equations, put together mass balances and spreadsheets, and that's always our starting point. But we also use biological process modeling to allow us to run multiple iterations without having to do all those hand calculations again. So this is a simple model that we set up using Hydromanus GPSX. It's one of the 3 main biological process models on the market. You can see we characterize the primary effluent. We have that going to an aeration basin, which within that aeration basin module, it is modeled now as a plug flow reactor, 5 different cells. And then we go to final clarifiers, and we put the filters in and we show the discharge. And within this model, we're able to adjust recycle flow rates, we're able to adjust airflow rates, different DO targets, to just see what our anticipated effluent quality would be. So the first thing we did with the model is we looked at to determine or confirm our required airflow rate. And the required airflow rate here was 10,630 CFM for a conventional activated sludge system. And the graphic here on the right is the required airflow by zone. And this is an output from the process model. So the Y, again, the x-axis says index. That's cells. So we kind of set this up in five activated sludge trains or cells in series to get that plug flow reactor. And not surprisingly, cell number 1 requires the highest amount of airflow. We have our highest oxygen demand, and so we're sucking up a lot of the oxygen in that particular cell. So keep in mind, or let's just keep that 10,630 number in the back of our minds, because if we had a traditional 5.4 MGD plant without all this extra loading from the industrial user, I'd probably tell you this airflow rate should be about 5,500. So what we saw here was approximately double what a typical municipal plant would be. So at design loading conditions, the required aeration volume resulted in a hydraulic residence time of 16 hours. It's not really excessive, but anytime we talk about a long detention time plus high BOD loading, we always have a concern that we're going to grow some filamentous bacteria and just give us a lot of heartburn when we go try to settle in our secondary clarifiers. So that's something that we definitely wanted to be aware of. So we evaluated adding selector zones. So you can see this was what I'm talking about. We have the 5 different cells. So 4 individual trains, 5 cells apiece. And so we looked at what if we didn't put diffusers in that first cell and we just put in mechanical mixing to really use that as an anaerobic zone and really take advantage of a kind of a BNR scenario or BNR layout. And what we found was that it dropped our aeration horsepower from about 350 horsepower. So that was per blower that we had on site to 250 horsepower blowers. And we had 2 of those for a duty point. So it did reduce a lot of our horsepower for aeration requirements. And we know that selector zones can also provide multiple benefits. I just discussed the decreased energy consumption. The reason we looked at it to begin with was for the decreased filamentous growth. And then we know could be some improved treatment. We know that, anaerobic conditions, we take up a lot of BOD there. So, hey, that could help us out in the aerobic zone. Plus, the big driver is that in the future, it sets the stage for future BNR. It's pretty easy to bring in a mixed liquor recycle and route that back to take advantage of maybe some future nitrate removal. So what we found, again, this is a output from the model. On the y-axis is airflow, and on the x-axis is the different zones. So implementing an anaerobic selector zone resulted in a 23% decrease in the required airflow at the design conditions. So you can see in cell number 1, airflow is 0. That's because we turned the air off with the model. We made that the anaerobic zone. And then cell 2 becomes our first aerated cell, and it requires about 3,600 SCFM as compared to the previous scenario when we ran it conventionally. Our first cell seeing the wastewater needed about 4,800 SCFM of air. So we did find the energy savings, and we did find the BNR benefits by putting in that anaerobic selector zone. And then we were able to prove with the model that BNR can be achieved at design conditions without an optimized BNR system. I mean, we didn't set out to make this a BNR plant, but we did take advantage of what the layout gave us and what the data gave us. So the first graph here on the bottom left, again, a model output, zones across the bottom, orthophosphate concentration in the reactors on the y-axis. So you can see cell 1, we go into our anaerobic selector zone. We have the phosphorus release. We're up to greater than 35 milligrams per liter of orthophos that's been released. And you see that as we move through the end of the basin. By the time we get to the end, we're well below 1 milligram per liter of orthophosphate. Saw a really similar approach with nitrate. Our effluent nitrate was stuck around 4, and our anaerobic zone was really bigger than it really needed to be. So it did serve as an anoxic zone. It helped remove the nitrate, and then also provided that environment for the PAOs to thrive. And then you can see by doing that, we didn't affect our effluent ammonia in any way. So again, no ammonia removal in that first cell. We're still about 13, 14. But by the time we get to the end of the plant, we're less than our 2 milligram per liter effluent limit by far. So some key components of the existing infrastructure was maintained to provide operations flexibility. This is one thing that we always try to do when we go on a plant site is what's currently existing that we can use in the future. And so I think earlier I hit on the fact that this facility used to be fed by an influent distribution channel where we were able to, primary effluent would go straight down the middle and be divided between the 6 different cells. We still wanted to give them that opportunity to have that flexibility. You know, if something goes on and we want to operate in a Johannesburg or some other kind of arrangement, we're able to take our effluent, or sorry, our primary effluent, and instead of going directly into the anaerobic zone that we've defined at cell number 1, we can still run down that middle distribution channel and put all of our influent flow into cell number 2. Or another option we have here is some step feed settings. If we want to feed into cells 1 and cells 2, we can do that. And then finally, you see the future recycle channels I have highlighted here. Those were the old effluent channels that the wastewater flowed through. So the concrete was still in good condition. So we kept those active and put new gates on there, because in a future BNR scenario, all we have to do to get nitrate removal is simply put a recycle pump at the end of the basin, you know, run 50 foot of piping and drop that into that recycle channel. Then we have the ability to send that mixed liquor recycle back to cells 1, 2, or 3, simply by opening a gate. So we were able to take advantage of that existing infrastructure and, you know, spend a little bit of money to rehab it that really gives us some benefit if we have to make that conversion to BNR. So operational flexibility allowed for implementation of BNR. So what you're seeing on this screen here is just some things we did with the walls. So the red flow path is how the system is currently operating. So the 6 smaller cells you see there, those were the existing cells, and then the big cells you see at the end were the new aeration volume that we added. And so we put holes in the wall to where we could effectively take off bits and pieces without taking a whole process train offline. So if something happened in the 3 cells on the left, like you see here, they're down, I'm still able to push a lot of flow through and take advantage of my new back cells by putting some holes in the wall and having some gates. And conversely, in the green routing, I could run everything through the 6 existing cells and then take advantage of the volume on the back right-hand side. And so by having those recycle gates and having gates separating the process, there are multiple configurations for biological, phosphorus, and nitrogen removal. So obviously the AO process is kind of how the system is set up now. Primary effluent comes into the anaerobic zone. The RAS gets recycled there as well. But with just a few modifications and really minimal equipment, we can go to the A2O process, which gets us nitrate and phosphorus removal. And then if something's not working there, we need to optimize or change our processes, we can run the Johannesburg process, which allows our RAS to come into a dedicated anoxic cell, and then our influent comes into the anaerobic zone in cell number 2. And just kind of from a visual how that could be actually put into practice. Again, the AO process, this is how we operate now. RAS comes in along with primary effluent to the anaerobic cell, and we flow on through. Everything else is aerobic. But in the future, if we want to make this A2O, I mentioned earlier, we put a mixed liquor recycle pump in at the end, take advantage of that existing effluent channel that we're naming a recycle channel. And that gets our mixed liquor recycle back into cell 2, the anoxic zone. And we're still bringing our primary effluent and our RAS into our anaerobic zone. And then if we need to do Johannesburg process, we can bring our RAS only into that anoxic zone. We can turn off the diffusers or turn off the airflow in cell number 2 and route our primary effluent straight to that to get our anaerobic zone. And then again, still have our mixed liquor recycle to take care of some of the nitrate issues that we may see in the future. So the plant is now up and running. It's in compliance, and the operating staff is gaining some very valuable experience prior to future nutrient limits. Since they are not required to report phosphorus or nitrate or any of that, I do not have any data to share with you to prove what the model results showed, but I can tell you that they are passing their BOD, TSS, and nitrate or ammonia limits with flying colors. So I guess some of the key points to end with here, we always want to begin with the end in mind. If there's any kind of project that we're going to get involved in, and we want to think about what might be required in 20 years, and is there anything we can do today, you know, relatively cheap's not the right word, but relatively cost effectively, that will save us a lot of heartache or heartburn in the future. So just because we don't have nutrient limits in your permit doesn't mean that there's no advantage to a BNR approach. And we saw in Sulphur Springs, by implementing the AO process, we saved a significant amount of energy, and we did see some advantages from filamentous growth, and really confident that we are seeing that phosphorus and nitrogen removal right now. So in the case of Sulphur Springs, by doing the BNR approach, I mentioned we were able to go from 350 horsepower blowers to 250 horsepower blowers. This resulted in a significant capital cost savings that more than paid for the anaerobic zone mixers. Those mixers were, I think, 5 horsepower invent mixers, so very efficient, relatively low horsepower. And the savings we got from downsizing the blowers paid for those mixers, and then we get to take advantage of the operating costs going forward. And then I keep beating myself to the next point, because the lower airflow demand and the smaller blowers, the annual O&M costs are lower. And so kind of wraps it up. If you guys have any questions or want to know more, I did not update this slide with the proper date or the project name, so apologize for that, but that's my email address. So if we have time for questions now, I'll take them, or you can just shoot me an email if you want to talk about this any further.
Yeah, thanks, Rusty. Anybody have any questions for Rusty? Definitely welcome to send in some emails, but yeah, if you have something now, then don't be afraid to shoot it in the chat or just speak on out. Looks like we have a shy crew today, Rusty.
Well, you know, Tom Myers retired, so he's the guy that I could always count on to ask some questions or harass me a little bit from the back. So since he's retired, I guess life just got easier.
We'll find somebody to fill his shoes. No worries. So, well, great. Well, yeah, if anybody has any questions, just shoot them on up. Thanks, Rusty. Really appreciate it.
You bet.
Well done. Sounds like a good project, and took it in the right direction. Neat.
All right, appreciate it.
Hey. All right. Well, we will take just a couple minutes here. Let's see. Shelly is our next presenter. I see Shelly on the line here.
She just sent me an email saying she's waiting in the lobby.
Oh, gotcha. Okay. Yeah, we can fix that. So. Okay, Shelly, can you hear us now?
Oh, can you guys hear me okay?
Yep, we can hear you. So.
Thank you.
Right. Well, if you need a couple minutes to get ready, if not, you should be able to share your screen now, but
good deal.
Just
yeah.
Whenever you're ready.
Just a second. Can you remind me again where to go on Zoom? Where I'm used to using Teams. Can you remind me where to go to share screen? Oh, there it is. I've got it. Thanks.
There you go. Yeah, no problem. So
Okay, how's this look? Can you guys see the blue and green presentation?
Looks
yep,
great.
we can see it.
Okay, wonderful. So the time I've got, it looks like we've got until 11:10. I'm going to run through this. I will tell you I'm new to the blue and green company as well as chart. So there may be some technical questions I might not be able to answer. But if not, you know, I can certainly take down your name and your information and follow up with you later. Before I get started, is there anybody on here that's familiar with the blue and green technology?
Yes, we have one of your systems at my plant.
Oh, great. Okay, wonderful. So yeah, we'll talk about some of the plants where we've got installations in. You guys may be aware, but Blue and Green back in November was acquired by Chart Industries. So Blue and Green is now part of the Chart Industries family, which basically allows them to kind of leverage the Chart offerings as well, which would be tank systems and things like that to offer them together to municipalities for ozone applications. And so, you know, this is one of the favorite slides that we like to use at Blue and Green. And it's just, you know, that we're all here because of our combined resource that we value so much, and that's water. And how can we transform that water into, you know, a safe resource for all of us, that wastewater. And so I think for some of you who are familiar with the blue and green technology, this might be, you know, too much, but for those of you who might not be familiar, blue and green basically utilizes Henry's law. So they pressurize, they take a liquid side stream and they bring it in from where the blue and green logo would be down here, like a lagoon or whatever that is. And they bring that in, and then they pressurize the gas together with the water. And that results in a side stream dissolution. And so water serves as the barrier to kind of limit undissolved gas from escaping. The only way for the gas to get out is to dissolve in that water. So that results in very high concentrations of gases in the water. And it also, because of its efficiency, allows for a much smaller carrier stream. So it can potentially save lots of money, electricity. It can result in smaller, you know, smaller piping, and that can save the municipality money too. And so I know that, you know, we've got all the different technologies, biological processes, and et cetera, but let's, I think the main focus today is just on ozone. So I'll stop there and just see if anybody has any questions on this particular slide or the technology in general. Okay, there are no questions. I'll continue on this. So our system for ozone, we call it the high DAWS system, but we also offer a streamlined system, which is basically kind of like a bare bones. It doesn't have as many bells and whistles as the high DAWS does, and that would include, you know, certain panels or possibly ways for us to monitor it remotely and things like that. And so what they offer is an unparalleled ozonation of water and wastewater. So they eliminate the DPP issues, they minimize the discharge of emerging contaminants. So applications would be in disinfection, obviously, advanced oxidation, taste and odor control, or sludge reduction. And I think most of you are familiar with how ozonation works, so I'll skip past some of these. This is, you know, background on ozone and how all that works. Here's an installation map, which is pretty exciting, although ozone is one of the areas that we're not as much in yet, but it's because it hasn't been a big focus for blue and green, and that's starting to change now. But right now we have 5 installations in the US for ozonation. We have over 100 installations in the rest of the US for the rest of our technology. So ozone is probably, you know, our newest one. And then Blue and Green's value proposition is obviously utilizing Henry's law, but that we can optimize transfer efficiency. So this results in a smaller footprint, like I mentioned, smaller piping and ancillaries, and also consuming 20 to 40% less of the molecules, which, you know, especially with some molecules like CO2 being harder to come by. Of course, that's not in the ozone system, but you know, that saves the municipality money. And so initially, you know, some of these systems may appear to be a lot more on the front end. They may be double or, you know, as much as 30% to double what the competing systems are out there. The real value is if we can speak with the municipalities or with you as engineers or operators and just talk about the full life cycle cost, which of course for some municipalities isn't as important because maybe they use cash method of accounting or whatever, where it's really the money up front that's more important. But that's where we rely on guys and gals like you to make sure that the municipality understands the true value of this technology is not just in the money you might not save in the beginning, but it's really in the life cycle cost and saving on molecules. So here's an example which many of you might be familiar with. It's the Fayetteville oxidation wastewater disinfection. So we have 2 high DOS systems installed here. We worked with CH2M Hill. It was a 13 MGD and 29 MGD peak for this plant. And so you can kind of see the layout here and how it looks, and I'll show an aerial here in a minute. This is actually quite a small system, and it's sitting on top of these very large concrete basins. And so oxygen generators have since been replaced with on-site liquid oxygen storage due to the premature fouling of ozone generators. So we did have some trouble initially with that. But ozone's very effective in the reduction of contaminants. And for the city of Fayetteville, this was very important to them because they wanted to be able to look to the future and, you know, have that as an option if they wanted to turn up the system to basically help them eliminate emerging contaminants. They have that option. Any questions here on this system? Okay, we'll move on here. And so these are just more about the Fayetteville system, but let's move on to the next one. Okay, and here's a picture of how Fayetteville is situated, the aerial photo, and this little white part in the very bottom right, that is the blue and green system. So it didn't take up very much room, considering
That's not the system.
That's not the system? Oh,
Nope,
is it?
right there.
Oh, it's up here, sorry. Thank you, I've been there. You think I know where it was. Okay, yeah, it's sitting on top of the concrete basins here. Okay, yeah, you guys are more familiar with that. Do you want to offer any comments on the system?
Not at the moment, I'll let you get through it.
Okay, all right, thanks. So another one that we did was the Clarksville oxidation. So it was ozone for primary disinfection. It was a 16 MGD plant, and the application was primary disinfection. So that was installed in 2015. So some of these are kind of older installations, and we have made some improvements since then on the technology. Another application that we had was in Putin Bay. There's some misspelling up here, but Putin Bay is a small island community on Lake Erie. So basically the only way that they could get drinking water was from the lake, and they had been experiencing issues with cyanotoxins. So when the Ohio regulators came in and required that they implement treatment, they turned to the blue and green system, which was very effective in eliminating cyanotoxins. Any questions there? And then there's the last one I'll go over is just the Louisville one, which was an oxidation iron control. So they were having problems and utilizing ozone for various treatment objectives within the facility. So One routine use is for minimizing iron in the recycle stream for residual solids lagoons. So they had a planned project to dredge the lagoon, and there were concerns over the excess iron. And you can see here the effect that ozone has on the color and oxidation and iron. So showed some great improvements there. And then finally, just to mention again that, you know, as Blue and Green has grown and also become acquired by CHART, we're happy to support joint proposals where we can present CHART systems in line as well with Blue and Green technology. And to compare some of the, you know, foam jacketed systems out there. So the vacuum jacketed versus the foam tanks, there's a lot of efficiencies that can be gained, and also the life cycle is just so much better. So the foam tanks, you can't really, you know, it's not really worth it to even repair them after the end of their life. But with CHART tanks, that is an option. So you have just more hold time, superior performance, lifespan, all that stuff. So, yep, that's everything that I had. I guess I finished a little early. Do you guys want to go over any questions?
I had a couple questions. I saw on a slide earlier you said that ozone is relatively unaffected by solids and things in the water.
Yes.
Further up, I was wondering, is that based on like the treatment of the fecal coliform or overall?
Well, I think it has to do with the Blue and Green technology as well, because our Blue and Green technology just, we can operate even if there is a lot of solids, and that's just the unique function of the technology itself.
Okay, I was just wondering if they could quantify that, like how is the system? Do they know how the system affects the solids in the water or other parts of the treatment process when introducing ozone to, say, a stream that has a lot of turbidity in it?
That's a good question. I'm sorry, I don't know the answer to that, but I will see if I can find out. Okay. I know that, you know, as far as some, you know, biological compounds go, I mean, we have the rupturing of the cell walls that occurs during disinfection. So obviously that would allow if it's breaking apart those microbes, then, you know, they're not going to continue to grow, right? So you'd have that reduction in that sense, but other than that, I might have to dig into that a bit more.
Okay, I was just wondering if it was when that statement is directly if they're just trying to quantify fecal coliform kill, or if they study its effects on other aspects of the process, such as reactions with ammonia and phosphorus and BOD that could be left over from the treatment process.
Yeah, that's a very good question. If you don't mind, if you could just email me after this with your contact information, I'll be happy to follow up on that.
Okay.
Shelley, there is a question in the chat there.
Okay.
Michael asked, does disinfection of the primary of the Clarksville project affect the rest of the process?
I'm not sure exactly how it would affect what by the rest of the process. What process are you referring to?
I am not certain. You may have to type in some more comments there. So.
Oh, does it kill the good bugs? I am not quite sure about that. I'm still honestly, I'm you know, still learning about the technology and how it works. So Michael, I'll put in the chat, I'll put my email, and any questions that I'm not able to answer today, I'll work to follow up with you and get you an answer. Okay.
Yeah, does anybody have any other questions for Shelley?
Do you have any drinking water ozone applications, or is it all wastewater?
Well, yes, we do have drinking water applications. So we have applications for oxygenation, which are typically used in industrial applications like where they have a natural biological process that might need more dissolved oxygen. And then, so we have our SDOX systems for that. And then we have our CDOX systems, which are more for pH control. So CDOX systems use CO2 and basically create carboxylic acid. So that's a replacement for anywhere where people might be using sulfuric acid or strong acids to affect the pH of a system. And so sometimes that's used in water facilities as well.
Do you have any installations at water plants?
Yes, we do.
For ozone?
Oh, for ozone, yes. So we have 5 installations. Ozone is the newest one of the blue and green technology. It's one that's been around, but it's not one we've really focused on until recently.
I mean, at water plants, not at wastewater.
Oh, at water plants where they're ozonating the drinking water, yes.
Yes.
We do have some. Mm-hmm.
Okay.
Yeah, and I don't see any more questions in the comments on the chat, but I do want to thank you guys all for your time, and thanks for being patient with me as I'm, just trying to learn the blue and green technology and all the different nuances of the ozone applications.
Thanks, Shelley. We appreciate it. I know this was geared more towards the high DOS and the ozone. Yeah, we have heard and experienced really good things with the SDOC stuff. So very efficient, very, pretty quick ROI depending on your application. So that's good. Good. Okay, well, yeah, let's see. Shelley has her contact information there. If anybody has any questions, now's your time, or just jot that down.
Yeah, thank you so much. Thanks for the opportunity to talk to you guys today. Have a great St. Patty's Day.
All right. Thanks, Shelley. Appreciate it. Okay, let's see. Almost 11 o'clock. We're running a little bit early, but I would guess most people are okay with that. Is our next presenter, is Wen on board?
I don't know. She said she had a class, and that's why she requested the last spot. So
okay,
we have 20 minutes. We could do the business meeting.
Yeah. Does anybody have any objections to that? I think that'd be a good use or swap of the time. So, all right, I'll try to share my screen here. Whoops, there we go. Okay, did that share my screen?
Yeah, I can see it.
Yeah, looking good.
Okay, good stuff. So, all right, so we will go ahead and proceed with the business meeting. I guess we'll call this business meeting to order at 10:58. If you can see my screen here, this is just the minutes from the last meeting, and this is also recorded, and you can see that in the YouTube video from the last meeting. You can always reference it there. But yeah, the minutes from February 17th just covered a lot of announcements, information. We did get 3 direct training hours for water and wastewater out of the last meeting. Today will be 4 hours apiece. Yeah, if you can see that screen there, I don't have to read all this word for word, but presented the treasurer's report, announced about training hours, submitting that information. And there was no additional items, and we adjourned that meeting at 12:10. So, but I would consider a motion to accept the business meetings as presented from February 17th. I would do that in the chat. Oh, Stacy's got a motion. Anybody second?
Second.
All right. And if there's any opposed, then just please oppose in the chat there. And we can address those concerns. So for today, and a special thanks again to all the presenters. I know that not all the presenters are still on board, but we really, really appreciate the support, providing us the opportunity, the networking connections. We really appreciate it, taking the time out of your schedules. And we, like I mentioned before, we're approved for 4 direct training hours from ADEQ, and we will also submit 4 direct hours for the 2 ADH. But please keep in mind that in order to do that, we cannot do it off of just the attendance roster from Zoom. You need to fill out the training log, and we will send another copy of that today. You probably have one in your email from last month as well, but you need to fill out a training roster like listed here with the meeting date, your organization name, have your supervisor's name and a signature there. And the big reason we have to have you do this is so we get everybody's proper last name, but associated with the training ID, and then make sure each individual signs it. And after everybody from your organization that attends or that watches this recording after the fact, document it there, and you could submit that. And then once we get those in email, just email them to the district, and we will get those documented and submitted to ADH for you for all those members that are in paid status. And we don't have the date of the next meeting yet, but we will be emailing that out. We'll get that finalized and let you know as soon as we have that scheduled. And we will get the training hours posted on the website. So kind of in a transition period, but we will get those posted. And I do not have any additional business at the moment unless anybody has any questions.
I had something to say, Mayo.
Yeah.
So with the 6-month extension, I got an email from Sandy with DEQ. She said any hours that you receive after the, I think it's June 31st or June 30th, basically if you get any hours during the extension that applies to this renewal cycle, you cannot count those hours on your next cycle. So if you use those 6 months that they added, you can't use any of those hours for the next renewal, basically. So for your next license renewal, you only have 1.5 years to do it. Unless you get your training, all your training done before, then you can just submit it, and any hours after you submitted your renewal can count for the next licensing period. Does that make sense?
I think it does. I think that's a good point. So, and does anybody else have any questions about that? Okay. Yeah, thanks, Austin. So, yeah, and that's Sandy with ADEQ is the point of contact for them on the training hours. Good. Any other additional business that needs to come forth? Sorry, my apologies. I do not have a treasurer's report to present to you today, but there will be no changes on that. We'll definitely present one next time. So if there's no other items, then I would entertain a motion to adjourn this business meeting.
So moved.
Okay, got a motion, a second.
Second.
All right, motion and a second. So if you have any objections, please please share those in the chat. So okay, so that'll wrap up the business meeting, and keep an eye out for some emails with more communication from the district that'll be coming out. Let's see, stop my screen here, and we will see as soon as Wynn gets out of class. We'll just take a quick 5-minute break or so here. Wait for her to get out of class, and we will hop back on as soon as we're ready. So just hang tight. Yeah, if anybody needs to step away for a few minutes, feel free to do so. We'll we'll try to get things kicked off at 11:15 again. Get us back on track.
May, our next presenter said she's in the waiting room.
Okay.
Should be good to go now.
Oh, great. Wynn, how are you doing? Can you hear us? So I couldn't hear you there. I may have caught the last little bit, but.
What about right now?
Oh, there we go.
Great. I just unmuted myself. I guess that helped. How are you?
You're good. Doing well, thanks. Well, yeah, if you need a few minutes to gather your thoughts or whatever, I know you're running place to place, but take all the time you need and just whenever you're ready, share your screen.
Okay. Oh yeah, I guess
Should be.
I can do that. Yep. Let me do. Okay, can you see it?
Yep, we can see it.
Perfect. Stop that. All right, then I guess we can get started. Well, thank you for inviting me to talk. I'm very happy to share what we have gotten so far. And I know many of you probably have heard the stories on the news or know the concept that we're doing this, but hopefully this presentation could give everyone like a better understanding of why we can do this and how we're doing this. So the topic is wastewater surveillance for the spread of COVID-19. And let's see. Okay, so here,
hey, Lynn, sorry to stop you there.
Yeah.
I think we're looking at one of your, okay, there we can see the main screen there. It was kind of splitting your slides in half for some reason.
Okay.
Like it's sharing your notes screen instead of the actual presentation, but.
Yeah, I was wondering if I can just do the, well, let me see. Maybe we just do that.
Mayo, I believe that you got the wrong. If you're in slideshow mode, you'll need to go back and share the screen. That's just your full screen. It's probably showing you both.
Are you talking about me or Austin?
Yes.
Okay. Okay, let me see. maybe new share.
Yeah, if you, let's see. So if you click share screen again, if you, I mean, you can put it in presentation mode if you want first, and then click share screen and make sure it's on the actual presentation pop up, so to speak.
So does this work?
We can make that work.
Or maybe
yeah,
I should jump
we
out
can
of
make
the.
that work.
I saw this happen last week.
Sorry, I can't really hear. Maybe I just do this. Would this be okay?
Voice settings, do something.
Yeah, sorry, Tim. I'm not sure why that was so jumbled, but yeah, that might work, Win. Just
Do you
sharing their whole
want just do
desktop.
this?
Yeah, let's try that.
Okay.
So.
All right. Maybe we'll just do this. Does this work?
That'll work.
Okay, great.
Yep.
So like I was saying, so everyone now, I mean, we're 1 year into this. So we all know this COVID-19 is transmitted through our respiratory systems. And right now we know that the virus is called SARS-CoV-2. And however, what many people don't know is once people get infected with this virus, you can actually find viral particles, we call this viral shedding in fecal samples. And that means, whenever the fecal samples gets into the wastewater, we can hopefully, in theory, be able to detect this virus. And that's really how we got into this wastewater monitoring business. And here I showed two pictures. Hopefully, you can see the morphology of the viral particles a little bit better. And this left one is the TEM image, and you can see the protein exterior of the virus and also the spikes on the surface. So right side, it's just a cartoon illustration of what the virus looked like. And what really mattered to us is that the interior right here. So that's the genetic material carried in a viral particle. And this one is RNA. And later I'll show you more about, the structure of it and all that. So how we do this, I guess, study is, first we would collect our wastewater samples. And if people with COVID-19 release their, fecal samples into the wastewater, we should be able to detect that. And we would take it to the lab and then basically, depending on what kind of samples we're dealing with. So if we're dealing with the raw sewage, so we should have a relatively higher concentration of the viral particles, and we could do direct RNA extraction on the wastewater. Or if we're dealing with like effluent samples or in between treatment steps, at that moment, the virus concentration probably is relatively low. So we might need to do sample concentration step in order to accumulate more virus particles, and then we could detect it. And then the detection method right here, so it's called RT-qPCR. So that's reverse transcription quantitative polymerase chain reactions. It's a mouthful, but later I'll show you, how exactly that's being done inside the instrument. And once we get the results out, it's basically showing us the relative abundance of the viral particles in, a particular sample. And hopefully, if we monitor wastewater for a long time, and we could establish like a baseline of the viral concentration. And then if there is a spike coming, we would be able to, hopefully alarm the public and telling people, hey, it seems like, we can already detect this, even though the numbers of infection has not shown this yet. And that's really what this disease surveillance is all about. And of course, you can use the data in other models to assess the risk and, all that. Okay, so before I show you, exactly how things are done, so I do want to give you a little background knowledge on molecular biology. So this slide, I show you the structure of the nucleic acids. There are two types of nucleic acids out there. One is this deoxyribonucleic acid, because it's the deoxy, which means it actually, don't only carry this H right here, while the RNA, which is the ribonucleic acid, it carries this OH. You can see comparing these two, the structure almost look identical. It's just, with the RNA, it has one more oxygen, and here it does not. And in our, bacteria cells or in our human cells, we have DNA, and we also have functional RNA as well. But in the virus, especially for the SARS-CoV-2, they only carry the RNA inside their protein shells. And with the DNA, it's all like double strand. So you can see they are bonded with these hydrogen bonding. And hopefully you can see these are pretty small, but we have C, G, and AT. So these are all the nitrogen bases carried on the DNA or RNA structure, or molecules. And so C can bond with G with 3 hydrogen bonding, and A can bind with T with 2 hydrogen bonding. And basically, the reason I'm talking about this is because in our PCR process, if you start with the DNA, you actually will need to break up these hydrogen bonding to deal with a single strand DNA. With the RNA, it seems like we don't have that step, but we actually need to convert RNA first to complementary DNA and then carry out the PCR process. But I'll show you that in a minute. So our first step, once we get the wastewater in our lab, is however we can isolate or purify the RNA from the samples would be the first priority. And you can imagine now there are many things carried in wastewater. So we know there's, BOD, nutrients, solids that we need to remove. But in addition to all that, inside the cell, nucleic acids is just one part of the cell or the viral particle. And there are so many other components, like here we were showing you, there's the protein shell, the membranes, and inside the cell there are, other material as well. So it's quite an ordeal to extrapolate just the RNA part. There are actually 2 main ways to do RNA extraction. And here I'm showing you the 2 pretty common methods right now being used. And the first one is this extraction by centrifugation. And how this is done is, we would start with the wastewater sample, and then we would add the cell lysis solution. Basically, the purpose of that is to open up the cells or the viral particle that can expose the RNA and also other interior material to the solution. And afterwards, we would pass the solutions through a filter. So right now, you have the filter here, and hopefully, the RNA plus other cellular materials are all caught on this filter. And then we would do centrifugation a few times, and then all the liquid portion will be carried over, through the filter, but the RNA and other things are being left on the filter. And then we would add a washing solution into this, this tube. And then the washing solution hopefully will carry all the unnecessary material in our next step and leave only the RNA particles on this filter. And after that, we would do a couple more centrifugations. So here you can see the optional step of centrifugation or washing. So this is all really just try to get as much of the RNA in its purified form as possible. And then the next step is called elution. So this eluting step, what we do is we add a liquid with components inside that can bind to RNA. And because of the binding, they can actually pass through the filter. So when you do the centrifugation, the liquid carrying the RNA will get past the filter. And then we can throw away the top filter part, And this liquid here we get is the RNA extracts that can be used in the next step. So this is actually what we use in our lab. And then there's another, I guess this part B shows a relatively newer method in terms of RNA or DNA extraction that is no longer using the centrifugation as the separation technique, but they are using magnetic bead in order to attract the RNA and extract the RNA. So how this works is, we still start with the wastewater sample, and you still need to add cell lysis solution in order to open up the cell or the particle. And then you would add the solution that carries the magnetic beads inside. And whenever you have the magnetic beads, it actually being functionalized or coated with different bonding that can bind with the RNA. So once that happens, then if you apply a magnet right here, so all the particles will go to one side and you can extract the unnecessary liquid and dispose that. And the next step is similar to our centrifugation method where we wash the RNA, because at this step, they still carry other cellular materials. And after a few washing cycles, and hopefully, when you get rid of the liquid and leave only the beads, you would only be carrying the beads with the RNA on there. And then after you dry the beads, and then you also add the eluting solution, basically that will release the RNA from the bonding on the magnetic beads. And then when you apply the magnet again, so this way you can remove the beads and leave only the RNA in the solution. So both of these are quite popular right now. There are many commercial kits available. So we're using the kit from QIAGEN, but I know there are many companies that are making the magnetic beads, and I guess the results have shown they are equally effective. And then, we would take this extracted RNA right here and put it in our PCR instrument. And before I show you how the PCR is done, and I do want to show you the central dogma. I don't know how much you remember from your biology class, and this is the central dogma of molecular biology or genetics. So this figure perfectly illustrates how the our genetic material get passed down to our next generation, as well as how the proteins are synthesized and also expressed. So here we have, depending on what kind of cells you have, and if you have bacteria or mammalian cell, we would have DNA. And like we said earlier, if you have viral particles, many times we have RNA to begin with. And if you do the, how we pass down the genetic material, that's through DNA replication. And how it's replicating itself, it is through these hydrogen bonding. So they are very specific, kind of like, right now, about our vaccines to this virus, and that's also fabricated based on this mRNA, which is the messenger RNA. So from the DNA to RNA, and this is a process called transcription. And when you separate your double-stranded DNA into a single strand, and again, through these hydrogen bonding, you can make messenger RNA. And the messenger RNA is a really important intermediate step in order for the new cell synthesis, or like the protein synthesis, because from messenger RNA, there is a component that's not shown here that's called tRNA, which is called translation RNA. And from the translation RNA, they can make different amino acid and then form different proteins. Now, the reason, so originally, this is the material flow, from DNA to RNA and then to proteins. But when you start with RNA on its own, now in our PCR machine, they can only deal with the DNA for polymerase chain reactions. So you actually need a step which is called reverse transcription. So from the RNA, first, you actually convert it back to its complementary DNA, also through the hydrogen bonding. And then you can, use this complementary DNA to carry out the amplification and then do the analysis. So here, this next slide, I showed you 3 different processes, and you probably hear all these words and wonder, okay, what exactly is the difference? So the instrument we use is called PCR, which is short for polymerase chain reactions. And this column B right here showing, it's called quantitative or real-time PCR. So that's short for, or I guess it's mostly referred to as qPCR. And the word quantitative means, we can get the relative abundance or the concentration of a particular gene, like the SARS-CoV-2 that we're interested in right now. And how this is how this works is, you start with the double-stranded DNA, like we were showing earlier, as the nucleic acid structure. And the first step is called denaturization, which is separating the 2 strands. And then when you only have one single strand, then you would need to subject it into 2 processes. One is called annealing, the other is called extension. So what it is really, in the solution, you would also supply material or I guess substances that can allow the DNA to synthesize, and this would be the direction. So the orange line would be the new DNA. And then, when the new DNA are made, they also have these fluorescent signals or molecules that can express or emit the fluorescence. And the machine actually will be able to capture the fluorescence and have the quantification on that. And later we can convert this fluorescent signal back to the concentration of the DNA. So you might say, okay, why do we have to do all these steps in order to measure the concentration? Why don't we just measure the concentration directly? Now, the main reason is many times, especially in environmental samples, the concentration of these genes, no matter we're talking about DNA or RNA, they are really low. And directly measuring it, you probably don't have enough fluorescent signal in order to quantify it. So that's why, through these denaturization, annealing, and extension, we actually are making millions and billions copies of your original DNA or RNA. And that way, the quantification part will be way more easier or accurate. So this is the qPCR part. And then for the RNA particles, like the virus, we actually have to do this reverse transcription or RT-PCR. So how this works is, you start with an RNA strand instead of the DNA strand. And first, you actually need to make this cDNA, which is the complementary DNA strand. And then from this step on, it will be very similar to your original quantitative PCR. So you make millions of copies of that. And then by measuring the concentration of this, you can go back to the original RT, I guess the RNA. So when you put these 2 together, that's what this process is about, or the method we're using for this study, which is the reverse transcription quantitative PCR, the polymerase chain reactions. So you can see, you first start with the RNA, make the cDNA, and then you would subject it to, a similar process like this. So you have denaturization, you have annealing and extension, and then you have the fluorescence bond to the cDNA, and then you can measure the signal. So how do we, or I guess, what does the result look like? Or how do we measure the signal? So these figures showed you an example of that. So if you look at this A and B, you see whenever you supply enough material in order to make new DNA. And the first is the initialization phase. Basically is, we are trying to get ready and we are doing the denaturization step. And once the replication starts, and it will start as an exponential curve, basically. And hopefully we want to catch the beginning of this exponential curve because that shows the original concentration of your DNA or RNA. And how we record this is basically, when your fluorescent signal passes a threshold, and that's the number, so the cycle number. So we would, when we make make copies of the DNA or RNA, you can imagine, 1 become 2, 2 become 4, 4 become 8, 16, all that way. So each cycle we'll call, 1 cycle number. And then a typical PCR process, we would have 35 to 40 cycles, sometimes even longer, like 45 cycles. So the earlier you can detect the fluorescence in your cycle number, that means you have more DNA or RNA to begin with. And the larger the cycle number, let's say if you record a cycle number that's 35 or 38, that means you have a very tiny amount of your original RNA or DNA to begin with. So once we get different cycle numbers, and then we will translate this onto a plot. So when we do the PCR, each plate we run, we need to include a standard curve, and which means we are putting in a known concentration of the DNA or RNA in your target, and then we would run it at the same time as the unknown samples. And with these known concentrations, and we could also record the number of your cycle number, like the CT or CQ. And then when you plot the cycle number with or versus your concentration number, and you would get a straight line here. And what that means is later, for the unknown samples, if you read, you have 25 as your cycle number, and coming to the standard curve, you can find the corresponding concentration of your genes, and this would be the relative abundance that we try to measure. And up here, I put a standard curve of our own. So this is one of the primer we use, which is called N1 for this particular virus. And you can see, we put in a known concentration starting from 20 gene copies per well, all the way to 200,000 gene copies per well. And, we get a pretty good standard curve with the R-square value larger than 0.099, which means it's a really good fit. Everything worked out. And then, with the unknown samples, they're mostly in between 30 and 40 cycles of the standard curve. So we can find, the corresponding concentration of the genes. So next, I'm going to show you a snapshot of what the data we got or what it looks like. So we have collected samples from Northwest Arkansas and the Central Arkansas. So initially we're just focusing on the influent samples, and right now we're focusing on both the influent and the samples within the treatment plant. So after each treatment step, what kind of concentration we're dealing with. And here you can see the minimum and maximum and average concentration for a particular plant. And this is in gene copies per mil or milliliters of our wastewater. And you can see, sometimes it's really low, like it's only showing like 30 or 40 gene copies, or in some plants, like the Prairie Grove plant, we weren't able to detect anything with the, I think, 3 samples we got from them. And then we definitely sampled Fayetteville a lot more than other places like Nolan plant and Westside plant. So thank you, Tim and Austin, for your help on this. And, we have over 30 or 40 detections, and almost, I think after last September, I'd say the majority of the influent samples, we were able to detect the concentration. Although the concentration, it doesn't seem like there are huge spikes in them. So the concentration seems to stay always around like thousands gene copies per mil kind of level. And right now, when we've also sample from, let's say, after primary sedimentation or after secondary treatment or after the whole treatment, the final effluent. And what we were able to see were after the primary sedimentation, we also can pretty much consistently detect the virus, but after the secondary treatment, the majority of the virus are gone. And also in the final effluent, we could barely detect anything in terms of this particular virus. So that means, all you guys, we're doing a good job in our wastewater treatment. Basically, we're removing the majority, and if not all, of these viral particles from the wastewater. So that's really good news in terms of the environmental spread of the virus, because at least we're not supplying another source of the virus into our environment. So this is my last slide, and I'd be happy to answer any questions you might have. Yes, we are still continuing the effort to measure the virus, and we really want to establish like a long-term database for this. So in the future, if there is a need to try to look at the potential spikes in the data, then we can alert the public a little bit earlier, because right now it seems the research is showing the wastewater data can show the signal 3 days to 5 days ahead of the the testing results. So yeah. Any questions?
I've got a question.
Sure.
Excellent presentation. So is Prairie Grove just better than everybody else?
No. Well, so in terms of the viral concentration, it seems like there are many factors that can impact can we detect this or not. So the timing we grab the sample. Now sometimes we take grab samples, sometimes we have composite samples. I'd say definitely composite samples are what we prefer, but in certain cases we can only get the grab sample. So I'd say there is a higher chance of detection in composite samples than the grab samples. And also, just about how much of the population are affected in the community that this particular plant is serving. So you can imagine if there's, I don't know, 2% of the people versus 0.2% of people that are infected, then there's definitely a better chance of detection for the 2% versus the 0.2%. So it's really difficult to say, like, do we happen to sample at the time when there's really low release into the Prairie Grove wastewater? I mean, we just don't know, unless we can consistently trying to measure like for 3 months and trying to see like, we absolutely not see anything from that plant or not.
Thank you.
No problem.
Yeah, anybody else have any questions for Wynn? No, that was a good presentation. Really appreciate it. Yeah, glad there's a lot of smart people like you, all that deep chemistry and stuff like that. So
yeah, we're very happy to be able to do this, because for me it's also something new too, because in the past I've only dealt with bacteria, that's what we focus on in our biological treatment, but it turned out, hey, we could do the viral detection as well. So that's good.
Good. Well, yeah, a bunch of people in the chat here say thanks. Lane says thanks, and very well done. So yeah, anybody else? No. Okay, well, we have your contact information.
Yes.
If anybody, we can get that to them and they can reach out to you, and we appreciate it very much.
No problem. Yeah, well, thanks again for inviting me, and really, like, my numbers or email address are available, so if you later think of something you want to ask, and hopefully I can provide an answer to you, but if I can't, I can at least direct you to someone I know that knows more than I do.
Oh, sure, great, thanks. So
yeah.
Okay, well, thanks, Wynn. Appreciate it.
No problem.
And yeah, as far as the rest of the meeting, that's all we had on the agenda. So, I mean, we'll hang out for a few minutes, but if anybody, in case anybody has any questions or anything else, but yeah, I think that's all we had for today.
Great. Yeah, well, thank you guys. And I guess I'll talk to you later then.
All right. See you.
Thank
Wayne.
you, Wynn.
Thanks.
Thank
Bye.
you.
Okay, everybody. Well, have a good day. Appreciate it. And yeah, sorry, Mike. We'll work on those lunches for next time, huh? Yeah.
Mayo, thanks to you and Austin and Zach for all your work on putting these together. And this is very valuable and very good way to get this training. So we appreciate it.
Yeah, we're glad it's able to work out. So, and yeah, everybody keep in mind, if they have some presentations or anything they'd like to see, or somebody has something to offer, just let us know, because we'll be looking for people next month as well. So thanks, Mark. All right. Well, you guys have a good day. Appreciate it.
See you, Mayo.